Hello there, and welcome to Physics with William, where curiosity settles into a comfortable chair and science takes its time. Tonight, we are following a question that at first sounds almost impolite in its refusal to behave. If light has no mass, why does gravity bend it anyway? It is one of those ideas that seems as though it ought to sort itself out the moment you say it aloud. Gravity pulls on things. Light is not a thing with mass in the usual sense. And yet, when light passes something enormous, something dense and heavy and powerful, it does not continue as though nothing has happened. It bends, not dramatically, not with the flourish of a circus act, but quietly, measurably, unmistakably. A beam that should have gone one way goes another. A star appears slightly out of place. The universe gives the impression that the rules have been followed, even though by ordinary common sense they seem to have been ignored. Before we settle into that strange little puzzle, I would love to know where you are listening from tonight, and what sort of hour has found you. Perhaps it is very late and the day has finally stopped asking things of you. Perhaps it is early, and the world has not quite decided what mood it is in yet. Perhaps you are listening from a city bright with windows, or from somewhere quieter, where the night outside feels wide and patient. There is something fitting, I think, about a question like this reaching people in different places at different times. Light itself is always on the move, crossing distances without a pause, and here we are gathered in our own small corners, trying to understand what happens when even light cannot pass entirely untouched. And if you find this soothing, or interesting, or simply a pleasant way to let the mind drift somewhere curious before sleep, I would be very grateful if you gave the video a like and perhaps subscribed as well. It helps this calm little corner of science find its way to others who may enjoy a gentler sort of wondering. I only hope the question does not keep you too alert, though if it does, at least you will be lying awake with gravitationally bent starlight for company, which is not, as sleepless thoughts go, the very worst option. Now then, let us begin with the trouble itself, because it really is a lovely bit of trouble. We grow up with a certain feel for how gravity works. It is the reason dropped keys head for the floor instead of floating toward the lampshade. It is why tea stays in the cup unless we become distracted and wave our hands too enthusiastically while making a point. It is why the moon circles the earth, and why our feet remain reassuringly committed to the ground even on days when the rest of life feels rather less stable. Gravity, in the ordinary picture, belongs to objects with weight. It acts on things that have mass. A bowling ball, a loaf of bread, a cat who has chosen the exact centre of the hallway at night. These are gravitationally respectable items. They behave in ways that make sense to us. Light, by contrast, seems like a different sort of guest altogether. It is not a solid object. It does not sit in your hand. It does not wait politely on a shelf. It arrives, it illuminates, and it carries on. Light pours across a room in the morning without asking permission. It slips between leaves. It flashes off glass. It reaches your eye and tells you what the world looks like. It is so familiar that we forget how odd it really is. We talk about rays and beams and flashes, as though we are speaking of some very delicate thread or stream, but that is only language trying to make peace with something that does not behave quite like anything else. And yet, despite that difference, gravity and light do meet. In fact, they meet all the time. Light from distant stars passes galaxies on its way to us. Light leaving the surface of the sun climbs out through the gravitational grip of the sun itself. Light near black holes does not simply go where it pleases. The cosmos is not a collection of neatly separate departments, where mass lives in one office and light in another and nobody shares paperwork. The universe is far less tidy than that, though in a very consistent way. Gravity has a say in the path of light, and the reason turns out to be one of the most important changes in how humans learn to describe reality. But let us not rush there, because rushing is how perfectly good mysteries get flattened into homework. Better to sit with the discomfort for a while and notice why the question matters. If gravity bends light, then gravity's doing more than just tugging on heavy things. It is not merely acting like an invisible hand pulling apples downward and planets inward. Something larger is going on. The old picture begins to creak. We start with a rule that feels sturdy, that gravity affects mass, and then along comes light, apparently massless, curving anyway, like a cyclist ignoring a sign that clearly said straight ahead. There is a very human tendency, when faced with that sort of contradiction, to suspect one of three things. Either the premise is wrong, the conclusion is wrong, or the universe has once again been needlessly clever. In this case, the answer leans firmly toward the third. The premise that light has no mass is not the mistake, at least not in the ordinary modern sense, and the observation that gravity bends light is not in doubt either. What had to change was the framework surrounding both of them. The question did not need a patch, it needed a different map. Still, the older map was not foolish. It worked very well for a long time, and it matches the way things feel in everyday life. If you imagine gravity as a force pulling on objects because they have mass, then you can understand quite a lot. You can understand falling, orbiting, and the general reluctance of furniture to remain aloft. You can explain why planets move the way they do, and why a thrown ball returns to Earth instead of pursuing a career among the clouds. In that picture, asking why gravity bends light sounds rather like asking why a fishing net catches moonbeams. It should not. The categories do not seem to line up. So perhaps the best place to begin is with a small act of imagination. Suppose you are standing in a very large, very dark hall. At one end, someone switches on a narrow lamp, and a clean beam cuts across the space from one side to the other. In your mind, that beam goes straight. Not because you have calculated anything, but because straightness is what light seems to prefer. It travels in lines. That's how we draw it in school diagrams, how we picture shadows, how we make sense of mirrors and windows and doorways left slightly open. Straight is the natural route. Now imagine placing something enormous nearby. Not a table or a wardrobe, but something with serious celestial ambition. A star perhaps, or something denser still. You do not need to picture the details too sharply. Just imagine that the space around the beam is no longer ordinary. In the old intuition, you might ask whether the massive object reaches out somehow and tugs on the light. But that phrasing immediately feels awkward. Tug what exactly? What handle does gravity grab hold of if light has no mass to offer? It sounds as though one should be able to object on procedural grounds. And yet the beam changes course. Not because it suddenly becomes heavy, and not because gravity has decided to make an exception. The route itself is altered. This is the subtle point, and it is one of the reasons the story is so satisfying. The deeper answer is not that gravity pulls on light in the same simple way it pulls on a stone. The deeper answer is that the stage on which both stone and light move is not as rigid and empty as it first appears. Space is not merely a blank container. It has structure. It has geometry. Near mass, that geometry changes, and light, which always follows the natural path available to it, follows that changed geometry. There, we are already tiptoeing toward the heart of it, though I promise we will approach more slowly as we go. For now, it is enough to notice that the puzzle begins to soften the moment we stop imagining space as a featureless emptiness. Because emptiness, in physics, has a long history of disappointing anyone who assumes it is simple. What looks like nothing often turns out to be something with rules. The night sky appears calm from a garden chair, yet it is full of motion. A still room seems empty until sunlight reveals dust wandering through it like tiny absent-minded planets. In much the same way, space can look like a passive backdrop until the universe reminds us that backdrops do not usually bend. This shift in thinking did not arrive all at once, and it certainly did not arrive because people were bored and fancied making gravity more complicated. It arrived because the older way of describing things, brilliant though it was, began to meet questions it could not comfortably answer. Light was one of those questions. So was the behaviour of planets under certain conditions. So was the deeper relationship between motion, space, and time. Eventually the old view, dignified and enormously useful, had to make room for a stranger one, not because it had failed entirely, but because reality turned out to be broader than it had seemed. There is something almost comical about how often science advances by discovering that the plainest sounding assumption was only locally true. We say things like objects fall downward, until we remember that downward depends on where you are. We say time passes equally for everyone, until very fast motion and strong gravity start objecting. We say light travels straight, until the universe places a star in the way, and quietly replies, usually. The world is full of rules that work beautifully until they encounter a larger rule standing just behind them with folded arms. You might wonder, then, why light having no mass matters so much in the first place. Why not simply shrug and say, gravity affects more than mass and leave it there? That would certainly save time, though it would rob us of an excellent evening. The reason the detail matters is that it forces precision. It prevents us from slipping into a lazy explanation. If light had ordinary mass, we might be tempted to imagine it as just a very fast, very tiny projectile being pulled into a curve, the same way a thrown ball falls into an arc. But that is not what is happening. Light is not a little glowing pebble. It does not age in the familiar way on its journey, and it does not carry mass in the sense that matter does. So if its path changes near gravity, the reason must tell us something profound about gravity itself, and it does. In fact, it tells us that our everyday language about gravity being a pull is, while often useful, not the deepest description available. That language belongs to our scale of life. It works for dropped spoons and orbiting moons, and the general management of existence. But when the questions become more delicate, when they involve light, or clocks, or black holes, or the shape of the cosmos, gravity reveals a different personality. It is less like a rope and more like a change in the layout of reality. Objects are not always being yanked. Often they are simply moving as naturally as they can through a world whose geometry has been altered. That can sound abstract at first, though it becomes friendlier with practice. After all, we already accept that routes depend on surfaces. If you walk across a flat floor, the shortest route between 2 points is a straight line. But if you travel across a curved surface, the most natural route may look curved when seen from somewhere else. Airplanes follow paths over the Earth that can appear bent on a flat map. Not because the pilots have become whimsical, but because the map is flattening something round. The curve belongs to the geometry, not to a sudden loss of navigational confidence. Light near gravity behaves in a way rather like that, though on a far grander stage. It is also worth appreciating how bold this idea is from an ordinary human point of view. We are creatures who evolved to throw things, catch things, avoid stubbing toes, and find our way home before dark. Our intuition is built for rooms, weather, roads, and perhaps the occasional staircase whose design we do not fully trust. It is not built for the geometry of space near stars. So it is not embarrassing that gravity bending light sounds wrong at first. In fact, it would be a little alarming if it sounded perfectly obvious. The universe has no obligation to be limited by the categories that help primates manage crockery. And there is another reason this question has a special charm. It is one of those rare scientific questions where the answer does not merely add another fact. It changes the style of thinking. That is always exciting. Learning that a certain planet has a certain number of moons is interesting. Learning that your entire way of picturing gravity needs revision is something else altogether. It is like discovering that the house you thought had 4 walls and a roof has, tucked behind one hallway, an entire observatory. The structure was larger than you knew. You were not wrong to live in it. You just had not seen all the rooms. By now, perhaps, the original puzzle is beginning to feel less like a contradiction and more like an invitation. If gravity bends light, then gravity must be about more than mass pulling on mass. If light has no mass, then its bending must come from the nature of the path itself. If the path changes, then space is doing something. And if space is doing something, then the universe is not assembled from objects moving through emptiness, but from objects and light alike moving through a fabric whose shape matters. Once that thought settles in, a great deal begins to rearrange itself. Still, we should be fair to the older intuition, because it is not entirely cast aside. There remains a meaningful sense in which gravity governs motion. Things do fall, planets do orbit, light does bend. What changes is the explanation beneath those observations. The modern picture does not deny the behaviour, it deepens it. One of the quiet pleasures of physics is that it often keeps the visible world intact while replacing the machinery behind the curtain. The apple still falls, the stars still shine, the sunrise still arrives, yet the interpretation of why any of it happens can shift so dramatically that it feels as though the universe has been retranslated. And since we are talking about light, it is hard to resist pausing for a moment over how strange a thing it is to begin with. Light is both so immediate and so untouchable. It reaches us from the sun in a matter of minutes, and from distant stars in journeys so long that the light arrives carrying history with it. When you look into the night sky, you're not seeing objects as they are in some universal present. You're receiving messages that have been travelling. Some began before cities rose where cities now stand. Some left their source before whole generations were born, lived, worried about the washing up, and vanished again. Light is what lets the universe be seen, and yet light itself obeys rules that steadily refuse to fit into the simplest boxes. That's why the question matters beyond the technical curiosity of it. To ask why gravity bends light is also to ask what sort of place the universe is. Is space passive or active? Is gravity a force in the old sense or a deeper shaping of reality? What does straight even mean in a world whose geometry can change? And how often do we mistake our local habits of thought for universal truths simply because the kettle boiled when expected and the chair remained on the floor? There is something quietly humbling in all this. The world continues to be knowable, but not always on first inspection. It invites understanding, though not always the kind we originally hoped would do. A child can notice that things fall. A physicist can learn to describe orbit. Another physicist can discover that even the description of falling was only part of the story. Each layer keeps the earlier one, yet alters its meaning. So when light bends in gravity, the event is not merely a curiosity about starlight. It is a clue that the universe prefers structure over simplicity, and depth over convenience. Soon we will need to step back and look at the older view of gravity more carefully, because only then does the newer one reveal just how remarkable it is. We will have to ask what people once expected light to do near a massive object, why that expectation seemed reasonable, and how observations eventually forced a more radical answer. We will have to move from the familiar picture of gravity as a pull toward the stranger, and more beautiful idea that what bends is not light alone, but the world through which light moves. And once that shift is made, much else begins to follow with it, from eclipses to black holes to the strange way the universe lets us see objects that would otherwise remain hidden. For the moment, though, let the central question rest in your mind exactly where it belongs, slightly unsettled and slightly amused. Light has no mass. Gravity bends it anyway. Not because the universe is inconsistent, but because our first instinct about gravity was not the final one, and that, as it turns out, is where the real story begins, with the old idea sturdy in our hands and the first signs that it may not be quite enough. It helps, before we lean too hard on gravity itself, to spend a little more time with the traveller in question. Light has a habit of sounding familiar right up until you try to describe what it is without borrowing half a dozen metaphors and hoping none of them complain. We speak of beams and rays as if light were a sort of shining thread. We talk about waves, which makes it sound watery. Then we talk about particles, which makes it sound like dust with ambition. And all the while, light carries on being light, perfectly content to ignore our preference for tidy categories. The reason this matters is simple. If we want to understand why gravity bends light, we first need to be clear about what kind of thing light is and what it is not. Otherwise, the mind starts smuggling in the wrong picture without asking permission. It imagines little glowing pellets being tugged sideways by gravity, or some ghostly substance with hidden weight, or a stream that somehow counts as matter when nobody is looking. None of those pictures is quite right. And when the picture is wrong at the beginning, the explanation gets into trouble almost immediately. So let us start with the plainest statement available. Light has no mass in the usual sense. That sentence is true, but it can also be misleading if it lands too abruptly, because it sounds as if light ought therefore to be insubstantial, irrelevant, or incapable of doing anything physical. But that is not how it works at all. Light has no mass, yet it carries energy. It has no mass, yet it carries momentum. It has no mass, yet it can push, heat, transfer information, and alter the state of matter. Sunlight warms your skin. A laser can move tiny objects in a laboratory. Light from distant stars can cross the galaxy and arrive bearing news from places no human will ever visit. A thing does not need mass to be physically important. Light proves that rather confidently every single day. This is one of those moments where ordinary language lets us down a little. In daily life, we often use words like weightless or massless to mean ineffective. If someone says an argument carries no weight, they are not praising its elegance. If a meal leaves you feeling light, that may be delightful, but you would not expect it to power a tractor. So when people hear that light has no mass, part of the brain quietly rounds that down to barely real. It begins to picture light as a visual effect rather than a participant in the world. Something decorative, a helpful illumination service, very pretty, very useful, but not quite the sort of thing that gets involved in the heavy business of physics. Light objects to that interpretation. Not loudly, because it is not the theatrical type, but firmly. Light is not a painted backdrop on the universe. It is one of the main characters. It comes from atoms changing their internal states. It carries energy away from stars. It presses outward from the sun. It triggers chemical reactions in plants. It frees electrons from metal under the right conditions. It delivers the colours of the world into your eyes, and, in more dramatic circumstances, can damage tissue, drive solar sails, and help us measure the structure of the cosmos. A massless thing that can do all that is not a contradiction. It is simply a reminder that mass is not the only ticket to physical relevance. There is another common misunderstanding worth clearing away, because it lurks behind this whole topic. People often hear that light has no mass, and imagine that it must therefore travel instantly or exist outside ordinary rules. But light is not infinite, and it is not exempt from structure. In fact, one of the most important facts in modern physics is that light in empty space travels at a specific speed, not faster, not slower, but at a fixed limit that turns up again and again in the laws of nature. This is not just a practical detail about optics. It is part of the architecture of reality. It tells us something about space, time, motion, and causation. And light is not merely moving through the universe. In a deep sense, it helps define the terms under which motion itself makes sense. That is already a rather dignified job for something with no mass. Still, the phrase no mass needs one extra bit of care. When physicists say that light has no mass, they do not mean that light is nothing. They mean more specifically that light has no rest mass. That phrase sounds technical, but the idea behind it is not too dreadful. Rest mass is the sort of mass an object has when it is at rest relative to an observer. A chair at rest in your room has mass. A book on the table has mass. A cat pretending to be asleep while listening for cupboard activity has mass. Light does not fit into that picture because light is never at rest in that way. It does not sit still waiting to be weighed. Asking for the rest mass of light is a bit like asking for the sleeping habits of a lightning bolt. The category itself is the problem. This is where the idea of the photon becomes helpful, provided we do not treat it too mechanically. A photon is the quantum unit of light, the smallest packet in which light interacts. That does not mean a photon is a tiny billiard ball glowing politely in the dark. It means that when light exchanges energy with matter, it does so in discrete amounts. A photon can be absorbed or emitted, it can carry energy from one place to another, it can transfer momentum. But it remains massless. So once again we're invited to loosen our everyday intuitions. The world at this scale is not built to match the furniture showroom version of reality. And yet, the photon is not some wild exception, invented simply to irritate common sense. It behaves with extraordinary reliability. It follows rules. It can be measured, counted, redirected, polarized, scattered, absorbed, delayed in materials, and sent across fibre optic cables carrying enough information to keep much of modern life noisily operational. We may not picture it comfortably, but nature handles it just fine. One useful way to think about light is to stop treating mass as the only reason something can have an effect. Consider the wind. The wind certainly involves mass because air has mass, but what matters to your face on a cold day is not the philosophical status of each molecule. What matters is that energy and momentum are being delivered to you in a very direct and rather discouraging manner. Light does something similar without relying on mass in the same way. When sunlight falls on a surface, it delivers energy. In some cases, it also exerts pressure, tiny though that pressure may be. This is not a metaphor. There are real experimental setups in which light pushes on matter. There are proposed and tested spacecraft concepts that use large reflective sails, not because engineers have suddenly become maritime romantics, but because light from the sun can transfer momentum. A massless traveller can still arrive with enough insistence to shove. That simple fact helps untangle the mistaken idea that gravity would need to grab some hidden mass inside light in order to affect it. The universe is not limited to interactions based on weight alone. Mass is one property among several. Energy matters, momentum matters, geometry matters. Once those facts are on the table, the old objection begins to lose its confidence. It is also worth noticing that light behaves in a way no ordinary massive object can fully imitate. You can slow a stone, you can stop a train if you have a plan, sufficient distance, and very patient insurance staff. You can leave a loaf of bread on the counter, and it will remain there with excellent consistency. Light in empty space does not do stillness. It is all journey. This makes it a peculiar kind of traveller. It is not a passenger who occasionally steps off at stations. It is the travel itself, always in transit, always moving at that fixed speed through the vacuum of space. That fixed speed is not just a dramatic flourish. It is deeply tied to why light occupies such a special place in modern physics. Before the full implications of relativity were understood, the existence of a universal speed for light was already making the older picture of the universe uncomfortable. If light behaved like ordinary projectiles, you would expect its speed to add and subtract depending on the motion of the source or the observer, rather like throwing a ball from a moving cart. But experiments and theory began pointing elsewhere. Light refused to behave like that. It kept the same speed in vacuum regardless of how one moved relative to it. This was not a minor inconvenience, it was a foundational disturbance. It suggested that the stage itself, space and time, might need rethinking. But we are getting slightly ahead of ourselves, and there is still more to say about why light feels so slippery to describe. Part of the difficulty is that light has a dual character. In some experiments it behaves like a wave, spreading, interfering, producing patterns of brightness and darkness. In others it behaves like a stream of discrete quanta, arriving in countable packets. Neither image alone is sufficient. This is one of those facts that students encounter with a mixture of fascination and low-grade betrayal. One had been hoping the universe would choose a lane. Instead, it offers a deeper rule in which the categories themselves need care. Now, none of that means light is mystical or beyond explanation. Quite the opposite. We understand an enormous amount about it. We know how it is generated in many contexts. We know how it interacts with matter. We know why different wavelengths produce different effects. We know why glass bends it, why mirrors reflect it, why atoms absorb specific portions of it, and why telescopes can collect it from astonishing distances. But understanding light does require discipline. It punishes lazy metaphors. The moment we reduce it to a tiny dart or a rippling liquid or a glowing dust cloud, it waits patiently for the next experiment and then proves the metaphor incomplete. This makes light unusually useful in physics because it exposes the weaknesses in our assumptions. Matter can sometimes let us get away with simplified pictures for quite a while. Light is less forgiving. It crosses scales. It links quantum behavior with large-scale astronomy. It forces questions about space, time, energy, and causation. When a theory has cracks, light finds them. Which is perhaps one reason the history of physics is so full of occasions where understanding light better led directly to understanding the universe better. There is also a practical reason light becomes central whenever we talk about gravity. Almost everything we know about the distant universe reaches us by way of light or its close electromagnetic relatives. We do not scoop up stars with nets. We do not lean out the observatory window and touch galaxies with a long stick. We receive radiation. We read the sky through what arrives. That means if gravity changes the path of light, gravity changes the way the universe appears to us. It alters not merely some technical detail in the equations, but the actual map of what we see. A star may appear slightly displaced. A galaxy may look stretched. A hidden mass may reveal itself only because the light behind it is bent in just the right way. The weightless traveller becomes the messenger, and the message has been folded by gravity along the way. At this point, someone might reasonably ask a stubborn question. If light has no mass and cannot be brought to rest, why even use the word traveller at all? Does that not risk making light sound too human, too deliberate, too much like a tiny commuter with a briefcase and a schedule? Perhaps a little, but the metaphor still helps because light really does move from place to place carrying something with it. It leaves one event and reaches another. A star emits light, space is crossed, a detector responds. In that broad sense, traveller is not such a bad word. It reminds us that light is never merely there. It is always from somewhere, heading somewhere, linking source to destination. And unlike many travellers, light wastes no time dithering over the route. In empty flat space-time, it takes the natural path available to it. That phrase is going to matter more and more as we move forward. Because when people first hear that gravity bends light, they often picture gravity reaching across space and dragging the light away from the line it wanted to follow. But a more careful description is waiting. Light follows the natural path. The puzzle is that near mass, the natural path is not what our ordinary flat intuition says it should be. The traveller is not changing personality. The landscape is not as straight as it looked. Even before relativity fully recast the story, there were hints that light occupied a special status. It was always the awkward guest at the classical dinner table. Newton himself, brilliant as he was, had one picture of light. Others favoured wave descriptions. Later evidence made the wave picture indispensable. Then quantum theory insisted on bringing particles back into the discussion, though not in the comfortable old sense. Through all of this, light kept refusing to be reduced to an ordinary lump of matter. It became increasingly clear that whatever gravity was, and however it worked, the answer could not simply be that light behaves exactly like a rock with unusual lighting. That is why the phrase weightless traveller is more than a poetic convenience. It captures something precise. Light moves. It carries energy and momentum. It obeys exact rules. It can influence matter and be influenced in return. But it does not possess mass in the ordinary resting sense that our intuition associates with gravitational pull. So if gravity affects light, and it does, then the explanation must reach deeper than the old slogan that gravity pulls on mass. The slogan was never entirely wrong. It was just incomplete. You can see this incompleteness in a simpler way by thinking about energy. In modern physics, energy is not an optional ornament. It is central, and light has it in abundance. A hot object radiates light because energy is being emitted. The sun shines because processes in its core ultimately send vast quantities of radiant energy outward. Your skin warms in sunlight because that energy is absorbed. If gravity has a relationship not only with mass but with the broader physical structure that includes energy and momentum, then suddenly light is no longer standing awkwardly outside the door. It belongs in the conversation after all. Still, even that wording is only part of the destination. To say gravity relates to energy is helpful, but not yet enough to explain bending in the deeper sense. It prepares the mind. It loosens the old grip. It tells us light is not beyond the reach of gravity merely because it lacks rest mass. But the full answer will ask us to go farther still into the geometry of spacetime itself, where mass and energy do not just pull on things but shape the very paths available. Before we get there, though, I want to linger for one more moment with the ordinary experience of light, because it is easy to forget how strange familiarity can be. Every room you have ever entered was made visible by light, arriving from somewhere and interacting with surfaces in lawful ways. Every face you have ever recognized reached you through reflected light. Every sunset you have admired was an effect of light scattered through the atmosphere. Every star you've ever seen was a message delayed by distance. Light is everywhere in experience and yet almost nowhere in direct intuition. We do not feel ourselves surrounded by electromagnetic fields and quantized radiation. We just say the room is bright. Perhaps that is why questions about light can feel so satisfying. They take something constant and make it strange again. They remind us that the obvious world is built from processes we do not notice until a good question interrupts us. Why is the sky blue? Why does glass sparkle? Why does light behave as both wave and quantum? Why does gravity bend it if it has no mass? These are all questions that start in common experience and lead, step by measured step, into the deep design of the world. So now we have our traveller in clearer view. Light is massless but not powerless. It does not sit still. It carries energy and momentum. It can push, heat, inform, reveal, and transform. It travels at a fixed speed in empty space and behaves in ways no ordinary object fully mirrors. It is described in modern physics not as a chunk of matter, but as a quantum of the electromagnetic field, a peculiar and very disciplined participant in reality. If gravity still bends it, then we must stop looking for hidden weight and start looking for a broader understanding of what gravity really is. That is where the older picture begins to feel both admirable and slightly cramped. Because if one starts with gravity as a force that acts in the straightforward Newtonian sense on mass alone, light becomes a problem to be patched around. One can attempt clever workarounds. One can imagine a partial effect. One can even produce estimates that point in the right general direction. But eventually the question keeps returning, patient as starlight, asking whether the trouble lies not with light, but with the way we have framed gravity. And once that question is allowed to stay in the room, it becomes harder to ignore that the path from Newton to Einstein was not just a change in calculation, but a change in what the universe was thought to be made of. For a very long time, Newton's picture of the universe felt so solid, so orderly and so triumphantly successful that questioning it would have seemed almost ungrateful. It explained falling apples, orbiting planets, tides, comets, projectiles, pendulums, and just about every other respectable moving object a person might care to study without setting fire to the laboratory. If the world was a grand machine, then Newton had found the gears. He gave motion a language of astonishing power. He took the unruly behaviour of bodies in space and turned it into a system that could predict where things would go and how they would get there. That is no small achievement. That is one of the great turning points in human thought. And because Newton's framework worked so beautifully, it shaped more than physics. It shaped intuition. It trained generations of minds to imagine the universe as a stage made of absolute space and absolute time, with matter moving across it under the influence of forces. Space was the vast, unmoving arena, Time ticked along the same for everyone, everywhere, like a universal clock no one had to wind. Gravity, in this view, was a force acting between masses. One object pulled on another across distance. The Earth pulled on the Moon, the Sun pulled on the planets. An apple and the ground were not merely having a private disagreement, they were gravitationally involved. It is difficult to overstate how convincing this picture was. It was not only elegant, it was useful in the most serious practical ways. It improved navigation, it guided astronomy, it gave engineers and scientists a common structure for understanding the physical world. Most importantly, it matched what seemed obvious. Things with mass attract one another. Heavier things exert more gravity. Distance weakens the effect. Very good. Everyone can go home satisfied. Then, rather inconveniently, light entered the conversation. Now, Newton himself had a strong interest in light. In fact, he did some of the most famous work in optics ever carried out. He studied colour, prisms, reflection, refraction, and the nature of white light. He was not dabbling, he was building foundations. Yet his view of light was not the same as the one that later emerged. Newton favoured the idea that light was made of tiny particles, often called corpuscles. That was not a foolish guess. In some situations, it made excellent sense. Light seemed to travel in straight lines. It could be reflected and refracted. Tiny particles did not sound outrageous. The trouble, as it so often does in physics, was that nature eventually demanded a more complicated answer than the first useful one. Still, if one imagines light as particles, a tempting thought arises. If gravity pulls on masses, and if light consists of little particle-like bits, might gravity pull on light too? It is a wonderfully Newtonian sort of question. Perfectly sensible, perfectly orderly. And yet the answer in that framework becomes awkward almost immediately, because one then has to ask what sort of particles these are supposed to be. Do they have mass? If they do, what kind? If they do not, why would gravity affect them? The neatness begins to fray. There is a historical subtlety here that is worth treating carefully. People sometimes speak as though Newton himself straightforwardly predicted the bending of light by gravity in the modern sense. That is not quite right. The idea that gravity might deflect light does fit naturally enough into a Newtonian style of thinking, if you treat light as particles, and later thinkers did indeed explore that possibility. But Newton did not hand us the full answer waiting to be polished. What he handed us was something both more powerful and more limited. He gave the world a gravitational framework so successful that any future theory would have to explain why it worked so well while also showing where it stopped being enough. That is what makes this period so interesting. Newton was not wrong in the way a badly written horoscope is wrong. He was incomplete in the way a map of one country is incomplete when you're trying to cross an ocean. Within its range, his system was magnificent. Planets really do move in ways his laws describe with tremendous accuracy under ordinary conditions. Objects really do fall and accelerate in ways his mechanics captures beautifully. But the deeper nature of gravity remained hidden behind the effectiveness of the equations. The theory worked before anyone fully understood what gravity truly was. And that hiddenness matters for our question. Because if gravity is simply a force pulling masses toward one another across empty space, then light becomes troublesome. A force requires something to act on. Mass seems the obvious candidate. Light appears not to qualify. The old story starts stumbling over its own success. The better Newtonian gravity works for matter, the more sharply it seems to exclude light. One can try to rescue the situation, of course. One can say that perhaps light particles possess some effective gravitational susceptibility, even if their status is unusual. One can imagine gravity tugging on them as they rush past a massive body, changing their direction ever so slightly. In fact, reasoning along those lines can produce a deflection. Not a completely absurd one either. This is one of those delicious scientific moments where the older framework can gesture toward the truth without quite reaching it. A Newtonian-style picture can hint that light near the sun ought to bend, But the amount it suggests is not the full story. It gives only part of the answer, because the deeper reason for the bending is not truly contained within the old framework, and that partial success is almost more interesting than total failure would have been. If Newtonian gravity had said something wildly impossible, it would have been easier to discard. But it did something subtler. It pointed in the right direction while telling the wrong story about why. Meanwhile, the 19th century was making life steadily less comfortable for the old view. Scientists studying electricity, magnetism, and light were discovering that these phenomena were deeply connected. Light was increasingly understood as an electromagnetic wave, not merely as a stream of classical particles. That was already a challenge for Newton's preferred optical picture. But the larger crisis concerned motion itself. If light was a wave, what medium did it move through? Waves in air need air. Waves in water need water. So what was waving when light crossed the vacuum of space? A medium was proposed, often called the ether, a subtle, invisible substance that was supposed to fill all space and carry light waves along. It sounds quaint now, but it was a serious attempt to preserve the older habits of thought. If waves need something to wave in, then surely space must be full of something. Yet experiments designed to detect motion through this supposed medium kept turning up disappointingly empty-handed. The universe was not cooperating with the furniture arrangement. At the same time, another odd fact was becoming increasingly unavoidable. The speed of light in vacuum appeared to be the same regardless of the motion of the observer. That was deeply uncomfortable for Newtonian intuition. In ordinary life, speeds add and subtract. Walk forward on a moving train, and your speed relative to the ground changes. Throw a ball from a cart and the ball inherits the cart's motion. All of that makes sense in Newton's universe, where time is universal and space is fixed. But light refused to behave like a thrown object. It remained stubbornly itself. Now the cracks were spreading. Gravity was one issue, light another, and the structure of space and time a third. But in truth, they were all becoming parts of the same problem. The old stage was no longer stable. The actors were behaving too strangely. Into this walked Einstein, and one of the most impressive things about Einstein's achievement is not that he produced a few clever corrections, but that he changed the grammar of the conversation. He did not merely adjust Newtonian gravity to make room for light in some improvised annex at the side of the theory. He rebuilt the way motion, time, and gravity were understood. The turn was not cosmetic, it was architectural. Einstein's first great step came with special relativity, where the constancy of the speed of light was taken seriously rather than treated as an annoyance to be tidied away. If light has the same speed for all observers in inertial motion, then space and time cannot remain absolute in the Newtonian sense. Something else must give, must. And what gives, astonishingly, is our intuitive notion of simultaneity, duration, and distance. Time is no longer a single universal river flowing identically for everyone. Space is no longer a passive container with fixed measurements independent of motion. The two become linked in a new structure, later called spacetime. That alone was enough to change physics forever. But it did not yet fully solve gravity. It did, however, prepare the ground. Because once space and time are no longer absolute, once the stage itself is no longer rigid and untouched by the drama unfolding upon it, gravity becomes newly suspect. Perhaps gravity too is not what Newton had imagined. The crucial clue came from a very simple and very profound observation, often expressed through what is called the equivalence principle. Einstein noticed that being in free fall and being weightless are intimately related. If you're inside a falling elevator, at least in the idealized thought experiment version, where health and safety regulations have politely stepped aside, objects around you would seem to float, not because gravity had disappeared, but because everything would be falling together. Conversely, in an enclosed space accelerating upward, objects would behave as though pulled downward by gravity, even if no planet were present. Acceleration and gravity, in this deep sense, began to look like cousins very nearly wearing the same coat. This was not just a clever trick of perspective, it was a doorway. If gravitational effects can locally mimic acceleration, then perhaps gravity is not an ordinary force at all. Perhaps it is something about the geometry of motion itself. And once that possibility opens, the question of light changes completely. Imagine a beam of light crossing a sealed, accelerating room. To someone outside, the room is accelerating upward while the beam continues on its path. But to someone inside, the light appears to curve downward across the room. That is an astonishing thought. No one inside needs to talk about masses being tugged by forces. The light seems bent because the frame itself is accelerating. If gravity and acceleration are locally equivalent, then a gravitational field ought likewise to bend light. This was one of Einstein's earliest insights into the problem. Notice how different this is from the Newtonian attempt. The point is no longer that gravity reaches out and pulls on a massive light particle. The point is that the very conditions under which motion is described have changed. The room, the frame, the geometry, the structure of the path, all of it is involved. Light is not being given a secret mass. The world through which it moves is no longer behaving like flat, indifferent emptiness. At first, even Einstein's own estimate of light bending captured only part of the full effect, because the complete theory had not yet been built. But the direction was now unmistakable. The problem of gravity and light was not going to be solved by tweaking the old force law. It required a new understanding of gravity itself. Then came general relativity, and with it one of the most extraordinary conceptual shifts in science. Gravity was no longer described as a force in the Newtonian sense. Instead, mass and energy tell spacetime how to curve, and curved spacetime tells matter and light how to move. That sentence, stated plainly, is one of the great triumphs of modern thought. It is not merely mathematically powerful, it is philosophically daring. It says that the universe is not made of objects moving around on a fixed stage. The stage participates. The geometry is alive to the contents of the cosmos. In this picture, the old question begins to dissolve. Why does gravity bend light if light has no mass? Because gravity is not fundamentally about pulling on mass the way a rope pulls a bucket from a well. Gravity is the curvature of space-time, and light follows the natural paths available in that curved geometry. Light is not exempt because exemption no longer makes sense. Curved space-time is not a policy from which only heavy objects suffer. It is the environment through which all motion unfolds. This is the real turn from Newton to Einstein. Newton asks what force pulls this object. Einstein asks what geometry guides this motion. Newton works with masses attracting across space. Einstein works with space-time itself as the active structure. Newton's universe is a grand clockwork. Einstein's is a shaped fabric of relationships, where straightness depends on curvature, and even the path of a beam of light can reveal the architecture of reality. What makes this shift so satisfying is that it explains why the Newtonian world works so well in the first place. In weak gravitational fields and at ordinary speeds, curved space-time behaves in ways that make gravity look very much like a familiar attractive force. The old story survives as an excellent approximation. Apples still fall, planets still orbit, engineers can still design bridges without consulting a black hole. Newton remains magnificently useful, but in more delicate situations, especially those involving light, clocks, high speeds, or intense gravity, the deeper structure shows through. And this was not merely a philosophical refinement, it led to predictions, real measurable ones. The path of light passing near the sun should bend by a specific amount, not just vaguely, not poetically, but observably. This gave the new theory something rare and splendid, a chance to prove itself against the sky. That eventual confirmation would become famous, though we are not quite there yet. For the moment, what matters is the shape of the intellectual journey. Newton gave the universe order through force, mass, and absolute space, and time. His picture was so good that it set the standard for what explanation itself ought to feel like. But when light became unavoidable, and when the speed of a light refused to play by classical rules, the old structure began to strain. Einstein's answer was not to insist harder on the original assumptions. It was to question the assumptions themselves. Space was not rigid. Time was not universal. Gravity was not merely a pull. And light did not need mass to have its path changed, because the path belonged to space-time, not to flat emptiness. There is something wonderfully human in that transition. We often begin by thinking the world is simple in the way our intuitions prefer. Then the world hands us a fact that does not fit. We resist a bit. We patch a corner. We rename a difficulty. And sometimes, if the difficulty is patient enough, it teaches us that what must change is not the new fact, but the old frame around it. That is what happened here. Light did not turn out to be an annoying exception. It turned out to be the clue. So when we ask why gravity bends light anyway, we are really asking why Newton's gravity, brilliant though it was, could not be the whole story. We are asking what happens when a massless traveller crosses a universe that is not flat and indifferent but shaped by matter and energy. We are asking how straightness itself becomes a local matter rather than a universal given. And once that question is asked in earnest, we find ourselves no longer in Newton's fixed arena, but in Einstein's curved one, where even a beam of starlight can quietly trace the hidden contour of space. One of the hardest habits to loosen in all of physics is the habit of treating space as nothing. It is such a natural assumption that most of us never notice we are making it. Space seems to be the gap between things. It is what remains when the furniture has been moved out, when the planet is not in the way, when the air is gone and the room has been emptied. We imagine it as absence with dimensions, a container without personality, a silent stage so neutral that it almost disappears from thought altogether. That picture is useful for ordinary life, which is probably why it survives so stubbornly. If you're trying to park a car, arrange books on a shelf, or avoid walking into the corner of a table in low light, space behaves very much like emptiness with measurements. It gives you room to move or does not. You judge distance, direction, and separation. Nothing in the kitchen strongly suggests that the geometry of the universe is waiting behind the kettle like a patient but slightly smug mathematician. Everyday experience encourages the view that space is just there, featureless and passive, like the blank page behind the handwriting. The trouble is that physics eventually asks more of the idea than daily life ever does. Once you begin talking about light, gravity, motion, and the structure of the cosmos, space can no longer hide behind its reputation for being uneventful. The old image of space as a kind of celestial storage unit starts to fail. It does not fail all at once, and it does not fail because scientists suddenly became interested in making simple things sound expensive. It fails because certain observations refuse to fit inside it. Light changes path near massive objects. Time runs differently in different gravitational conditions. Orbits do not always match the neat expectations of a flat, static arena. The universe keeps acting as though the background is doing more than background work. It helps, I think, to notice how deeply the idea of emptiness is tied to human perception. We are creatures built to notice objects. We spot fruit, faces, doors, weather, cliffs, and the regrettable location of coffee tables when walking at night. We evolved to care about things in space rather than space itself. The gap between the tree and the rock matters because we can pass through it or not. But the gap itself does not feel like a thing. It has no colour, no smell, no resistance in the simple sense, so the mind treats it as a lack. It becomes a blank. That is understandable. It is also, in deeper physics, not quite right. Even before Einstein, the story of space had already begun to wobble. The old Newtonian picture imagined space as absolute. This was not merely empty room on a grand scale. It was a fixed framework, the universal reference against which motion could be described. space existed independently of the objects within it. Matter moved through it, forces acted across it, and time flowed evenly alongside it. This was tidy, powerful, and extraordinarily successful, but it also encouraged the sense that space itself remained untouched by events, as though the universe could be rearranged infinitely without the arena so much as wrinkling its brow. Then came the problems. Light, as we have already seen, did not behave as a comfortable Newtonian object should. Attempts to imagine it moving through a hidden medium, filling all space, did not survive experimental scrutiny. The speed of light refused to conform to old expectations, and once relativity arrived, space lost its claim to being a passive, absolute backdrop. It became inseparable from time in a new and startling structure. Spacetime was no longer the stage on which physics happened. It was part of the happening. This change is easier to say than to feel. Most people, quite reasonably, hear the word spacetime and nod politely while internally keeping their original image of the ordinary space with a bit of time glued on like an afterthought. But the real shift is more radical than that. Space is not merely where things are. Time is not merely what clocks do. The two are woven into a single structure that determines how events are related. Distances depend on motion. Durations depend on circumstances. Straightness becomes local rather than universal. Once this is understood, or at least reluctantly allowed into the room, gravity begins to look different as well. Still, even space-time can sound too abstract if one approaches it too coldly. So let us try a gentler route. Imagine you're walking across a large field in heavy fog. If the ground is flat, then the most direct route between where you are and where you want to go is straightforward enough. Keep a steady heading and off you go. But if the ground is not flat, if it slopes, dips, rises, or curves in ways you cannot immediately see, then the natural path changes. What looks straight from your limited local perspective may, in the larger geometry of the terrain, be something else. You're not being pulled sideways by some hidden rope. You're moving through a landscape whose shape matters. That is closer to what modern gravity asks us to imagine. Not a force reaching through empty space in the old mechanical sense, but a geometry in which paths themselves are shaped by the presence of mass and energy. A planet does not orbit the sun because an invisible hand constantly tugs it around like a stone on a string in some cosmic schoolyard demonstration. Rather, the sun changes the geometry around it, and the planet follows the natural route available within that geometry. Light does the same. The important thing is not that light suddenly becomes heavy enough to qualify for treatment. The important thing is that the route is no longer embedded in flat emptiness. This is why space is not as empty as it looks. Even when it contains no air, no dust, no visible objects at all, it still has structure. It can be flat or curved. It can carry the relationship between events. It can determine what counts as straight motion. It can influence how clocks compare. It can, under the right conditions, distort the path of light enough for entire galaxies to appear stretched, multiplied, or ringed by the gravity of unseen masses lying between them and us. Empty it may look, inert it is not. There is also a subtler reason the word empty becomes misleading. In everyday language, emptiness implies the absence of consequences. An empty room does not push back. An empty road, at least in moments of great good fortune, offers you a clear journey. But physical space is full of consequences even where there seems to be nothing there. Electromagnetic waves cross it. Gravitational influences are encoded in its geometry. Quantum fields, if we go deep enough, do not regard the vacuum as a simple void at all. The absence of ordinary matter does not mean the absence of physical reality. It merely means that the reality present is not made of the familiar stuff we like to bump into. Now, one must be careful here not to turn space into some sort of cosmic jelly, because that metaphor, though often helpful at first, can quickly begin misleading. Popular explanations sometimes describe space-time with a rubber sheet and a heavy ball making a dip in it. This has its uses. It gives a visual sense that mass affects geometry and that other objects move differently in the altered shape. But it also smuggles in a problem because the rubber sheet itself is already sitting in another gravitational field. The ball makes a dip because gravity is pulling it downward into the sheet. One then risks explaining gravity using a model that secretly depends on gravity to work in the first place, which is the sort of thing physics prefers to avoid when possible. Still, the rubber sheet survives because it captures something important. Geometry matters. Straightness depends on shape. A path that is most natural in a curved setting can look bent from an outside perspective. If we keep only that lesson and politely excuse the rest of the metaphor from further duty, it remains useful enough to continue. Another reason space seems empty is that we are not built to perceive curvature in spacetime directly. We do not walk past a strong gravitational field and think, "Ah yes, the geometry here is altered a bit. Perhaps I shall tread carefully." We just say the object is heavy, or the planet is massive, or the thing falls. Human intuition reports effects rather than underlying structure. That is normal. It is only when measurement becomes precise, or when conditions become extreme, that the deeper picture forces itself into view. A beam of light bends near the sun. A clock on a satellite runs differently from one on Earth and must be corrected if you want navigation to work properly. The orbit of a planet departs slightly from what the old Newtonian model alone would predict. These are whispers from geometry, and what whispers they are. One of the loveliest things about physics is that the world often reveals its deepest truths not through theatrical explosions, but through very small discrepancies. A star is a little off from where it should appear. A clock is ahead by a tiny amount. A planet swings around with a slight extra turn. Those modest deviations can open entire new descriptions of reality. The universe does not always shout its secrets. Often it mutters them, and only the very patient notice that the muttering does not match the old script. There is also something quietly profound in the idea that space can have properties without being made of substance in the ordinary sense. We're accustomed to attributes belonging to things. A table can be wooden, water can be cold, bread can be disappointingly stale if one has forgotten it for too long. But space having geometry can feel stranger, because the mind wants geometry to be about where things are rather than what the between itself is like. Yet in relativity, the between is not a passive separation. It has measurable character. It shapes motion. It participates in cause and effect. This is part of why the phrase "the fabric of space-time" became so popular. It suggests something with connectedness and form, something that can be shaped and whose shape matters. Of course, one must not take fabric too literally either, unless one wishes to end up imagining the universe as a sort of celestial upholstery project. Still, as a broad guide, it has merit. Space is not a blank nothing. It has relations, curvature, and causal structure. Time is woven into it. Matter and energy affect it. It affects the motion of matter and light in return. The emptiness is busier than it appears. If all this sounds slightly unfair to common sense, that is because common sense was never trained for cosmology. Common sense is local. It is practical. It does not need to know how light behaves near black holes, or how the timing of satellites depends on relativity. It needs to know not to step into traffic and whether the pan is hot. We should not be scandalized when the universe turns out to be arranged more subtly than the needs of ape-descended grocery carriers required. In fact, it would be rather odd if evolution had equipped us with direct intuition for non-Euclidean space-time, while leaving us still capable of forgetting where we set down our keys. And yet there is something surprisingly accessible about the deeper picture once one stops demanding that space be visible like an object. After all, we are comfortable with many real things that are not directly seen in themselves. We do not see gravity as a coloured mist hanging in the air. We infer it from falling and orbiting. We do not see time itself wandering about the room carrying a clock. We infer it from change and duration. In the same way, We do not see curved space-time as a painted structure in the sky. We infer it from the behaviour of light, matter, and clocks. Reality often announces itself through patterns rather than appearances. That point becomes especially important once astronomy enters the scene. Much of modern cosmology depends on reading light that has crossed enormous distances. If space were merely a neutral void, then that light would tell a simpler story. But because space-time has geometry, the story arrives edited by the root. Light can be delayed, bent, magnified, or split into multiple images by the curvature around massive objects. Entire clusters of galaxies can act like cosmic lenses. Dark matter, invisible in itself, can reveal its distribution through the way it bends the light of more distant sources. We see what cannot be seen directly by studying how the geometry of space has guided the messenger. Now there is a deeply satisfying reversal in that. What seemed most empty becomes most informative. The gap between galaxies, the apparently vacant stretch between source and observer, turns out not to be a bland separation at all. It is part of the evidence. The root itself carries knowledge. To understand the universe, one must pay attention not only to the things but to the geometry between them. This also means that when we ask why gravity bends light, we're really asking why the supposedly empty region around mass is not just blank nothing. Why is the path altered? Why does straightness change? Why does a massive body affect not only nearby objects with mass, but even the root of a massless beam? The answer lies not in a hidden tug on light, but in the fact that the surrounding space-time is different from what our untrained eyes assume. Empty-looking does not mean geometrically simple, and perhaps there is a broader lesson tucked inside that. Human beings are forever mistaking transparency for absence. If something does not announce itself with noise or texture, we assume it is not doing much. Air feels like nothing until wind objects. Time feels invisible until age argues otherwise. Space feels empty until gravity and light together force us to reconsider. The universe, rather mischievously, hides some of its most important structures in what seems least substantial. So when Einstein turned away from Newton's force-based picture and toward the geometry of space-time, he was not replacing a clear mechanical explanation with an unnecessarily abstract one. He was recognizing that the old notion of empty space could not carry the full burden of the facts. Space had to become active in the description, not in the sense of a substance with moods, but in the sense of a structure with geometry that responds to mass and energy. Once that step is taken, light bending near gravity ceases to be an awkward exception and becomes an elegant consequence. The traveller is still weightless. The root is what changed. Soon we can look more directly at the idea that gravity is better understood as curves rather than pulls, because that is where the pieces begin to settle into a picture that feels not only more accurate, but oddly more natural once one has lived with it for a while. For now, it is enough to let the old idea of emptiness loosen a little. Space is not merely where things happen, it helps determine how they happen. It is not a vacant corridor stretching indifferently between stars. It has shape, and that shape matters. Even when it looks blank, even when nothing visible occupies it, even when it seems to be doing absolutely nothing at all, it is quietly deciding what counts as a straight path and what does not. At first glance, the phrase curves, not pulls, can sound like one of those scientific slogans designed to be memorable first and understandable later. It has a neatness to it that can make a person suspicious. After all, most of us have spent our entire lives experiencing gravity as a pull. We drop a spoon, and it falls. We jump and come back down. The moon goes around the Earth instead of wandering off to see the rest of the galaxy. The whole thing feels very much like pulling, so when physics comes along and says actually gravity is not really a pull in the deepest sense but a matter of curves, the immediate reaction is often somewhere between curiosity and mild annoyance. It can sound as though science has taken a perfectly good everyday word and replaced it with geometry for the sake of showing off. But this is one of those cases where the new language is doing real work. It is not there to be clever. It is there because the older picture eventually runs into trouble. The notion of gravity as a force pulling masses toward one another is wonderfully useful, and for everyday purposes it remains one of the best approximations ever given to the world. You can build bridges with it. You can predict the fall of objects. You can send spacecraft in sensible directions. It earns its keep. Yet when light enters the story, and when time itself starts behaving strangely in strong gravitational conditions, the word pull begins to look too small for the job. It captures the effect without capturing the mechanism. One way to see this is to think about what a pull usually means in ordinary life. A pull suggests something reaching out and exerting an influence. You pull a door open, a rope pulls a bucket from a well, a dog pulls at the lead because it has decided that whatever lies 10 yards ahead is of urgent importance and absolutely not open to discussion. In each case, the idea is straightforward. There is an object, there is a force, and there is change in motion because of that force. The world of hands, ropes, carts, and tugging makes excellent sense to us because it is built from direct experience. Newtonian gravity fits that intuition beautifully. The Earth pulls on the apple. The sun pulls on the Earth. The bigger the mass, the stronger the pull. The farther apart the object, the weaker the pull. That picture is so intuitive and so effective that it feels almost rude to question it. It seems to explain what needs explaining. If the apple falls, gravity pulled it. Very good. Everyone may now go and have lunch. The problem is that the universe kept presenting situations where the language of pulling became increasingly strained. Light bending near the sun was one. The small but persistent oddity in the orbit of Mercury was another. The fact that clocks run differently depending on gravity was another still. These were not giant disasters. The old theory did not collapse in a dramatic heap. It simply began to show that there were corners of reality where its deepest assumptions no longer gave the full story. And when that happens in physics, one often finds that the most ordinary sounding word in the theory is the one concealing the greatest difficulty. Pull was that word. What Einstein realized was that gravity could be understood in a radically different way if one stopped treating space and time as a fixed stage. In the Newtonian picture, space is there, time is there, and matter moves through both while forces act upon it. But in general relativity, space and time are not passive. They form a single structure, spacetime, and that structure is affected by mass and energy. A massive object does not merely sit in space producing a pull. It changes the geometry around it. It reshapes the spacetime nearby. Objects and light then move according to that geometry. This is where curves enter the story. Not curves as a decorative flourish, but curves as a description of what the world is like in the presence of mass and energy. Matter tells space-time how to curve, and curved space-time tells matter and light how to move. That sentence has become famous partly because it is concise, but also because it really is the heart of the matter. It tells us that gravity is not primarily a hidden force reaching across emptiness. It is the shape of the environment through which motion happens. Now, whenever people hear this, they tend to ask a sensible question. If gravity is really geometry, why does it still feel like a pull? Why do I feel pressed to the ground instead of serenely gliding through curved space-time with an expression of informed detachment? The answer is that our daily experience is perfectly consistent with the deeper picture. You feel what you feel because the ground is preventing you from following your natural path through space-time. That sentence deserves a moment because it sounds strange at first and then becomes wonderfully clarifying. In general relativity, the natural path of a freely moving object is called a geodesic. That is just the path that counts as straightest in the curved geometry, even if it does not look straight in the ordinary sense. If you are falling freely, you are following such a path. You are not, in the deepest description, being pulled in the old mechanical sense. You are moving naturally through curved space-time. What you feel as weight is not gravity acting on you directly. What you feel is resistance. It is the ground stopping you from continuing along the path you would otherwise follow. This reverses the usual intuition in a way that is initially almost offensive. We are used to saying that standing still on the ground means not moving, while falling means being acted upon by gravity. In the relativistic picture, it is nearly the other way around. A person falling freely is moving along the natural track allowed by the geometry. A person standing on the ground is being continually pushed off that track by the upward support of the ground. That is why being in free fall feels weightless. The body is not being squeezed by support forces, it is simply moving as space-time geometry allows. This is one of the reasons astronauts in orbit feel weightless. They are not beyond gravity, far from it. Earth's gravity is very much present where they are. They are in continuous free fall around the Earth, following the natural curved path available to them. The spacecraft and everything inside it are all moving together along that path. There is no floor pressing upward in the ordinary way to produce the feeling of weight, so they float. Once that idea settles in, the phrase curves, not pulls, begins to feel less like a slogan and more like a key. It explains not only why massive bodies influence motion, but why the experience of gravity can disappear in free fall even when the gravitational field is still very much there. A pulling force model struggles to make that feel natural. A geometry model embraces it from the start. This also helps with the question of light. If gravity were only a pull-on mass, light would remain an awkward guest. It has no rest mass, so why should it respond? But if gravity is curved space-time, then light no longer needs a special exemption or hidden weight. Light always follows the natural path available to it in space-time. Near a massive object, that path is curved because space-time itself is curved. Light is not being grabbed. It is following the geometry. That distinction matters. It is the difference between saying a carriage is dragged off course by some external hand and saying the road itself bends. In the first case, the carriage wanted one path and was forced into another. In the second case, the path itself is the issue. If you continue along the road, and the road curves, your route curves too. No extra tugging is required. In a curved space-time, light follows the nearest thing there is to a straight route, but straightness is defined locally within that geometry, not by the flat intuitions of everyday space. A useful comparison, though not a perfect one, comes from travel on the surface of the Earth. Suppose two people each believe they are following a straight line. If they are thinking in terms of a flat map, that idea may become misleading very quickly. On a sphere, the most natural large-scale paths are not the straight lines of flat geometry. An airplane can follow the shortest route between two distant cities, and on a flat map that route may appear curved. The aircraft has not become whimsical. It is following the geometry of the surface it is moving across. General relativity asks for a similar change in thinking, though in more dimensions and with time included. The shortest or straightest path depends on the geometry of space-time. Near a massive body, that geometry is not flat, so the path of a planet curves, the path of a falling apple curves, the path of light curves. These are not separate oddities requiring different ad hoc explanations. They are related consequences of the same underlying structure. Another advantage of thinking in terms of curves rather than pulls is that it explains why gravity affects time as well as motion through space. The old force-based picture says little about time itself. Time in Newton's universe flows evenly everywhere. Gravity changes motion, not the structure of time. But in general relativity, space-time is one connected geometry. Mass and energy do not merely affect where paths go. They affect the rate at which time passes in different regions as well. That is why clocks nearer a massive object run more slowly than clocks farther away. This is not an illusion, not a faulty mechanism, not a technical annoyance for very picky laboratory staff. It is part of the geometry. The structure of space-time near mass differs from that far away, and the passage of time is part of that structure. A pull can explain why an object speeds up as it falls. A curve in space-time can explain that, and also why time itself behaves differently along different paths. This is the sort of thing that makes general relativity feel less like a correction, and more like a complete rethinking. It does not merely add a note saying, by the way, light also bends. It replaces the old machinery with something deeper and more unified. The path of matter and the path of light become part of the same geometrical story. Time enters that story too. Free fall, orbit, lensing, time dilation. All of it belongs together. People sometimes worry that describing gravity geometrically makes it less real somehow, as though a force is a proper physical thing while geometry is just a mathematical description we invented because we enjoy giving ourselves headaches. But geometry in physics is not decorative, it is measurable. If space-time is curved, that curvature has consequences. Paths differ, clocks differ, light bends, orbits precess. Signals from satellites need correcting. The geometry is not imaginary because it is expressed mathematically. It is part of what the measurements are telling us. In fact, one could argue that curves are more physical than pulls in this context, because the geometrical description explains more of what we actually observe. It is not merely a metaphor, it is the framework that best matches reality. The path of Mercury around the Sun, for instance, is not perfectly captured by Newtonian gravity alone. There is a small extra turning of its orbit that the old theory could not fully account for. General relativity explained it naturally through the curvature of space-time near the Sun. That was not a poetic success, that was a measurable triumph. The same is true for the bending of light near the Sun. A Newtonian-style argument can point in the general direction if you pretend light is made of very fast particles subject to gravity, but it only gives part of the correct value. The full amount of bending comes from the space-time geometry itself, not merely from a force acting as though light were ordinary matter. Again, the difference is not academic, it shows up in observation. There is a deeper reason curves make more sense than pulls once one becomes comfortable with the idea. Pulls require a medium of influence that reaches across space. Newton himself was uneasy about action at a distance. The notion that one object could affect another through empty space without any intervening mechanism was powerful mathematically, but philosophically unsettling. General relativity changes the question. Instead of asking how the Sun reaches out and pulls on the Earth across a void, it says the Sun's presence alters the geometry around it, and the Earth moves according to that geometry. The mystery shifts from hidden force transmission to the structure of space-time itself, which is still profound but feels more coherent within the theory. Of course, no analogy survives unlimited use, and there is always danger in getting too attached to simplified pictures. One can overdo the road analogy, the globe analogy, the rubber sheet analogy, and every other classroom favourite. At some point one must accept that space-time curvature is its own thing, not a disguised version of a familiar surface. Still, these comparisons are useful because they teach the right kind of humility. They remind us that what counts as straight depends on the geometry you're moving through. Once that lesson is learned, the rest follows more naturally. There is also something oddly satisfying in how this view changes our understanding of falling. For centuries, falling seemed like the most obvious example of gravity pulling downward. Yet in the relativistic picture, free fall is the closest thing to natural uninhibited motion in a gravitational field. The real interruption comes from whatever stops the fall. The chair beneath you, the floor beneath the chair, the ground beneath the floor. All of that is the universe refusing to let you follow the path you otherwise would. Weight is not pure gravity making itself felt. Weight is support. That may sound like a technical distinction, but it has an almost philosophical neatness to it. The state that feels most passive to us, standing still, is in one sense the less natural one in a gravitational field. The state that feels dramatic, falling, is in another sense the freer one. Physics has a talent for these reversals. It takes the world we thought we understood and rotates the view just enough to show that our intuition had the roles partly swapped. Once you see gravity this way, many things become easier to place. Orbits are not constant battles between forward motion and a pulling force in the old intuitive sense. They are natural motions in curved space-time. Light near a galaxy cluster is not mysteriously tugged aside despite being massless. It follows the shaped geometry. Black holes are not simply places where gravity pulls very hard. They are regions where space-time is curved so severely that the available paths inward and outward are altered in an extreme way. Even the expansion of the universe becomes easier to talk about, because geometry is already part of the language. This does not mean we must abandon the word gravity in daily life and become tiresome at dinner. There is no need to correct every mention of falling with a lecture about geodesics unless one is determined to lose friends efficiently. The old language remains practical and usually sufficient, but when we ask deeper questions, especially the one that brought us here, the curved picture becomes necessary. Without it, light remains a puzzle. With it, the puzzle turns into evidence, and there is something else worth noticing. Curves, not pulls, does not make the universe less concrete, it makes it more connected. The old story separates space, time, matter, and force into distinct roles. The newer story ties them together. Matter and energy influence geometry. Geometry influences motion. Motion shapes what clocks and rulers reveal. Light, matter, and time are all caught up in the same structure. The cosmos begins to look less like machinery placed on a stage and more like a single relational fabric whose shape and contents cannot be discussed independently for long. That is a more demanding picture, certainly. It asks more of the imagination. It asks us to let go of the comfort of picturing gravity as an invisible hand doing all the work. But in return, it gives us something powerful. It explains why a massless beam can bend. It explains why free fall feels weightless. It explains why time slows near mass. It explains why the old theory worked so well in ordinary cases while still missing crucial details in the more delicate ones. So the phrase curves, not pulls, is not trying to erase what we observe. It is trying to describe what observation really points to. The apple still falls. The planet still orbits. The starlight still bends. The change is that the underlying reason is no longer a hidden tug on things that qualify, but a curved space-time through which everything moves according to its nature. And once that idea settles in, the next step becomes almost irresistible, because if curved space-time really can bend light, then sooner or later someone had to go out and look for the proof in the sky itself, with the sun in the way and starlight passing close by. Once the idea of curved space-time begins to settle in, the next question almost asks itself, very well, if gravity does not simply pull in the old sense, but instead changes the geometry through which things move, what does that actually look like when light is involved? Not in a textbook sketch with tidy arrows and a politely labelled star, but in the real universe, where light leaves a distant source, crosses an enormous stretch of space, and then passes near something massive on its way to us. What do we really mean when we say the light bends? What exactly is happening when starlight misses the straight road? The answer begins with a small but important correction to the way we usually picture a straight path. In ordinary life, straightness feels obvious. A hallway is straight. A ruler is straight. A beam from a torch across a dark room appears straight enough for most practical purposes. If something deviates from that line, we say it has been bent or deflected. That language works perfectly well in flat, familiar settings where space behaves in the quiet, dependable way we expect. But once the geometry around a massive object is no longer flat, straightness becomes local rather than absolute. Light is still following the natural path available to it. The difficulty is that, from the larger perspective we're using to describe the situation, that natural path no longer looks straight. That is the subtlety hiding inside the phrase bent light. We are not saying that light suddenly forgot how to travel properly and drifted off course like a distracted driver missing a turn because they were thinking about lunch. Nor are we saying that gravity reaches out, takes hold of the beam, and yanks it sideways like a cross-school master correcting posture. The better picture is that the route itself has changed. Near mass, the geometry is not flat, and so the path that counts as the most natural one through space-time is not what our old flat intuition says it ought to be. A useful way to approach this is to think about how much trust we place in sight. We are, after all, trying to understand light using creatures whose main business is seeing. If anything feels reliable, it is the idea that light tells us where things are. We look at a lamp across the room and assume the light from it travelled in a simple line to our eyes. We look at the moon and take its position as given. We look at a star and imagine that the line from there to here is uncomplicated. Most of the time, for most purposes, that is perfectly reasonable. But gravity complicates the route in just the sort of subtle way that vision is least prepared to notice. Light still arrives. The source still appears visible, yet the position we infer is not quite the position we would have guessed if space were flat all the way along the journey. This means that when starlight passes near a massive body, the star can appear slightly displaced from where it would otherwise seem to be. The light left the star, followed the curved geometry near the massive object, and reached us along a path that is not the one a flat universe would have provided. So we look outward and, quite naturally, trace the incoming light back in a straight visual line as our brains are inclined to do. The result is a slight mismatch. The star seems to sit in a place it is not exactly occupying in that instant relative to the mass distorting the route. That is what it means for starlight to miss the straight road. The road itself is not flat. The message reaches us by a route shaped by gravity, and our ordinary visual habits interpret the arrival in a way that reveals the bend. There is something quietly remarkable about this. For centuries, stars had been treated as fixed points in the grand background, at least compared with the much more obvious wandering of planets. Even after astronomy became far more precise, the stars still carried a kind of visual authority. They were the distant markers by which other motions were judged. Yet here was a new possibility. Even the apparent position of a star could be altered, not because the star itself had darted elsewhere, but because the space near a massive body had changed the path of the light on its way to us. It is one of those ideas that, once absorbed, permanently changes what the sky means. You're no longer simply seeing what is there, you're seeing what arrived, and the arrival has a history. To understand the effect more concretely, imagine a distant star lying almost behind the sun from our point of view. Under ordinary circumstances, the sun's glare makes that an inconvenient arrangement for observation. But let us ignore the brightness problem for a moment and focus on the geometry. The light from the distant star travels toward us. If the universe between the star and us were perfectly flat in the relevant sense, then the path would be the usual direct one, and the star's apparent position would match that route. But because the light passes near the sun, and because the sun's mass curves the surrounding space-time, the path changes slightly. The beam follows that curved geometry and reaches Earth from a slightly different direction than it would have in a flat space-time. So the star appears shifted. It is not a large shift by the standards of ordinary life. No one glances upward and sees the heavens sloshing about like furniture on a ferry. The effect is tiny, delicate, and measurable, only with careful observation. But tiny is not the same as unimportant. In science, a tiny deviation can carry the weight of an entire new worldview. This was one of those deviations. What is especially pleasing is that the phenomenon is not limited to stars near the sun. The same principle applies anywhere light passes near a sufficiently massive object. A galaxy can bend the light from a more distant galaxy behind it. A cluster of galaxies can bend the light from objects even farther away, distorting their appearance into arcs, smears, or multiple images. A black hole, given the right conditions, can alter the route more dramatically still. The effect is universal because the principle is universal. Mass and energy curve space-time, and light follows the available paths within that curvature. That is why gravitational lensing, as it later came to be called, is such an important idea. The word lens is useful because it connects the phenomenon to something familiar. An ordinary glass lens changes the path of light, because light travels differently through glass than through air, and the shape of the glass redirects the rays. A gravitational lens does not use material in the same way, but the result is similar in one key respect. The path of light is altered so that images can be shifted, magnified, stretched, or even duplicated. Nature, it seems, is perfectly happy to build optical devices out of geometry alone. Still, before we get to those richer and more dramatic examples, it is worth staying a little longer with the simpler case of starlight near a star like our Sun, because this is where the conceptual leap became clear. The old Newtonian picture, if forced into the conversation, could say something suggestive. If light behaved like very fast particles, perhaps gravity would deflect it a little as it passed by a massive body. That at least moved in the right direction. But general relativity predicted a larger effect, because the bending came not merely from a force acting along the path, but from the curvature of spacetime itself. The road was changed both in what we think of as space and in the deeper spacetime structure. The difference between those predictions was not large to the naked eye, but it was large enough for science to care very much indeed. This is one of the recurring themes in the history of physics. Two theories can seem almost indistinguishable in broad everyday situations, and then one very specific, very subtle test reveals that only one of them has the deeper architecture right. The universe does not always make theory testing easy. It often hides the crucial clue in some small effect that becomes visible only under carefully chosen conditions. In this case, the clue was the apparent displacement of stars whose light passed close to the Sun. Notice what an elegant test this is. It does not require touching the star, visiting the Sun, or constructing a celestial protractor of absurd size, though I am sure someone would have tried if given the budget. It only requires patient observation, careful comparison, and trust that the sky is stable enough for tiny deviations to mean something. You observe where the stars appear when the Sun is not in the way. Then you observe them when their light must pass close to the Sun's limb under special conditions. If the apparent positions shift by the predicted amount, then the path of light has been altered. If the amount matches general relativity, then Einstein has more than philosophy on his side. Even apart from its historical importance, there is something deeply satisfying about using starlight this way. Light, which had once been the source of the puzzle, becomes the tool of the answer. We began by asking how gravity could affect light if light has no mass. Now light itself becomes the witness that reveals what gravity really is. It carries the signature of spacetime curvature to us. It reports the geometry by arriving slightly askew. The messenger is altered by the route and thereby tells us what the route was like. There is also a broader lesson here about how astronomy works. We do not observe the universe in the direct tactile sense. We do not go out and handle nebulae. We do not knock politely on the side of a galaxy cluster and ask what its mass distribution might be. We receive signals, mostly light, broadly understood. The heavens are known through arrivals. Every image in astronomy is a record of what travelled, not a direct encounter with the source itself. So if the path through the universe can be altered by gravity, then astronomy must become, in part, an art of route reading. We're not just asking what emitted the light, we're also asking what happened to it on the way. That changes the tone of the cosmos. The sky is not merely full of distant objects, it is full of trajectories. Every photon that reaches a telescope has a history. Most travelled in ways close enough to what we would call straight that we can ignore the distinction for many purposes. But some have wandered through curved geometry near mass, and come to us carrying that distortion in their direction of arrival. Those photons are like travellers who took the mountain road instead of the plain, and whose muddy boots tell the tale even if they say nothing. One detail worth emphasizing is that the light does not experience a choice in the way humans do when deciding whether to take the scenic route. It is not confronted by a signpost reading left for flat space-time, right for curved, and then making a bold but questionable decision. The light simply follows the geodesic available in the given geometry. That is the point. It does not need to know about gravity in the old force-based sense. It does not need mass to qualify for treatment. It moves as the structure of space-time allows. If that structure is curved, the path is correspondingly curved. This becomes easier to accept once one stops imagining light as a tiny glowing object moving through a rigid container. The old intuition wants the container to stay fixed while contents are acted upon. General relativity asks for something more subtle. The container and the contents are not fully separable in the description. Matter and energy shape the geometry. Geometry shapes motion. Light is not a special exception to this arrangement. It is one of the clearest demonstrations of it. And because light is so central to astronomy, the bending of starlight ends up mattering far beyond the original puzzle. It lets us detect mass that emits little or no light. It allows galaxy clusters to reveal their gravitational influence even when much of their matter is dark to us. It magnifies background objects so that telescopes can see farther than they otherwise could. It produces beautiful arcs and rings in deep images of the cosmos, not because the universe is trying to be decorative, but because geometry has optical consequences. In a certain sense, gravity became a telescope. That phrase is not merely cute, it is physically true in important cases. A massive object can focus or redirect light from behind it in ways that increase brightness or create multiple paths to the observer. Under especially symmetric conditions, the effect can form rings or nearly complete circles of light. In less symmetric settings, it produces stretched arcs or duplicated images. These are not visual tricks in the dismissive sense. They are real consequences of curved space-time acting on the route of light. But it all begins with the much simpler and more conceptually pure case of a star's apparent position shifting because its light has passed near a massive body. That is the clean version of the story. No elaborate arcs, no multiplied quasars, just a small displacement in the sky, enough to say that the old straight road was not available after all. There is something almost modest about that. General relativity, for all its grandeur, first proves itself in this context not with fireworks, but with a tiny celestial sidestep. The star is not where flat space would have made it appear. The difference is small, but the implication is enormous. Space is not inert. Straightness is not absolute. Light is not exempt. Gravity is geometry. And because the effect is so small, it also teaches an important scientific virtue, which is patience. Not every profound truth comes with a dramatic sensory signature. Some require precision, comparison, and willingness to let tiny deviations overturn large assumptions. The history of science is full of such moments. This is one of the best. A fraction of a shift in the apparent position of stars near the sun's edge becomes a verdict on the architecture of the universe. At the same time, one should not imagine that the stars themselves are somehow being physically dragged around in their distant homes. That is another trap for the unwary imagination. The source remains where it is according to its own motion and location. What changes is our line of sight to the incoming light. The path between source and observer is what gravity has altered. So the apparent position changes because the arriving direction changes. This distinction is crucial. Astronomy is always full of such distinctions between what is out there and how it appears from here, and gravity-bending light makes that difference especially vivid. This also introduces a quiet philosophical complication. If the appearance of position depends on the geometry light travelled through, then seeing is even less direct than we casually assume. Not false, not unreliable in a crude sense, but mediated by lawful processes all the way down. Vision, whether personal or astronomical, is interpretation built on arrival. We infer the world from what reaches us. Usually those inferences are good. Sometimes, with enough gravity in the way, they need correction. By now, perhaps, the phrase "when starlight misses the straight road" sounds less mysterious and more descriptive. The light is not malfunctioning. the road is not straight in the larger sense we once imagined. The sun's presence, or the presence of any sufficiently massive object, changes the geometry through which the light travels. The apparent source position shifts because the route was curved. A beam that left one point and reached another did so along the nearest thing to a straight path available in a curved space-time. From the old flat perspective, that path looks bent. From the deeper perspective, it is simply the route the universe allowed. That is the beauty of the idea. It preserves order while changing understanding. The world does not become chaotic. It becomes subtler. Light still moves lawfully. Gravity still governs motion. The sky still tells the truth. But the truth is richer than the old picture allowed. Even the stars can appear out of place for good reason, and that reason can be measured. The next step, naturally enough, is to ask how anyone first managed to test such a delicate effect against the overwhelming brightness of the sun and the stubborn practical difficulties of observing stars where the daylight usually wins every argument. Because once Einstein had predicted the amount of bending, the theory needed the sky to answer back, and the occasion for that answer would come in one of the most famous observing campaigns in modern science, where an eclipse briefly turned the sun from a blinding obstacle into an opportunity. There is something wonderfully unfair about the fact that one of the most important tests of modern physics required the sun to stop being the sun for a few minutes. Under ordinary circumstances, the plan was hopeless. If you want to know whether starlight passing close to the sun's edge is bent by gravity, you need to see stars very near the sun in the sky. But the sun, in its usual blazing and rather overcommitted way, makes that nearly impossible. It floods the daytime sky with light, drowns the stars from view, and generally behaves like a celestial object with no interest whatsoever in subtle observational convenience. So for Einstein's idea to face its great early public test, astronomers had to wait for one of those rare moments when the moon steps neatly in front of the sun and briefly turns a bright obstacle into an opportunity. That alone would have made for a memorable scientific episode. But the story becomes even more remarkable because of when it happened, who carried it out, and what it came to represent. Science is often imagined as a clean sequence of facts, instruments, and results, all proceeding with the tidy confidence of a well-arranged laboratory bench. Real history is less well-behaved than that. It arrives burdened with weather, politics, personality, accidents, rivalry, war, and the general inconvenience of human life. Einstein's eclipse was no exception. If anything, it was a perfect demonstration that ideas about the structure of the universe must sometimes make their way through muddy fields, cloudy skies, and the emotional aftershocks of a shattered Europe. By the time the Great Eclipse Expedition was being planned, Einstein had already published the theory of general relativity. This was not a small adjustment to old physics. It was a new description of gravity itself, one that replaced the comfortable Newtonian picture of force with the more unsettling and far more profound idea of curved space-time. Mass and energy shape the geometry of the world, and matter and light move within that shaped geometry. The theory did not merely explain known effects in a different language, it also made predictions. One of the most famous was that light from distant stars passing close to the sun would be deflected by a specific amount. That mattered enormously. A scientific theory can be elegant, daring, and mathematically compelling, but until the world answers back, there remains a certain tension. Has the theory really captured something about nature, or has it only impressed clever people in rooms full of paper? Einstein's theory needed a test that was clear, visible, and precise enough to distinguish it from older expectations. The bending of starlight offered exactly that. There was, however, a complication beyond the sun itself. Europe had just emerged from the First World War, and that meant everything was more difficult than it should have been. Scientific collaboration had been disrupted. Travel was complicated. Resources were strained. The intellectual world, like the political one, was still sorting through damage, grief, resentment, and exhaustion. Einstein was German. 9. Some of the astronomers most important to testing his theory were British. That may not sound dramatic from the comfort of hindsight, but at the time it mattered. Ideas do not float above history in perfect innocence. They're carried by people, and people live in nations, institutions, loyalties, and wounds. This is part of what makes the eclipse story so compelling. It is not simply a tale of numbers matching theory. It is also, in a quieter way, a tale of science attempting to behave more nobly than the century around it. The key figure on the British side was Arthur Eddington, an astronomer of formidable intelligence and unusual temperament. Eddington was also a Quaker and a committed pacifist. During the war, that was not a socially convenient position. He opposed military service on religious grounds and faced the possibility of conscription. It is one of those odd historical convergences that a man under pressure for refusing to participate in war would become one of the crucial figures in verifying a German physicist's revolutionary theory just after the war had ended. The universe, it seems, occasionally arranges symbolism with a little more confidence than historians usually prefer. Eddington understood the significance of general relativity early and recognized that the eclipse offered a chance to test it. The plan, in broad terms, was straightforward enough to describe and rather less straightforward to carry out. During a total solar eclipse, the moon would block the bright disk of the sun, and stars near the sun's apparent position in the sky would become briefly visible. Photographs could then be taken of those stars. Later, their apparent positions could be compared with photographs of the same star field taken when the sun was elsewhere in the sky. If the stars appeared shifted outward during the eclipse by the amount Einstein predicted, then the bending of light would have been observed. This sounds satisfyingly clean until you remember that totality lasts only a short time, that precision astronomy is difficult even under generous conditions, and that weather is a profoundly unscientific collaborator. Also, the necessary comparison was delicate. The amount of deflection was tiny. The stars were faint. The equipment had to be transported to remote locations where the eclipse path would provide the needed view. Plates had to be exposed properly. Instruments had to behave. Temperatures had to cooperate. Cloud cover had to refrain from expressing itself too enthusiastically at exactly the wrong moment. In short, an immense theoretical gamble was being handed over to glass plates, fragile optics, and the sort of logistical planning that can be undone by a single patch of unhelpful sky. Two main observing teams were organised for the eclipse of 1919. One went to the island of Principe off the west coast of Africa, where Eddington himself would observe. Another went to Sobral in Brazil. This was sensible planning. If one site had bad weather or equipment trouble, the other might still succeed. In astronomical work, redundancy is not pessimism. It is experience wearing sensible shoes. The eclipse itself took place in May of that year. By all accounts, the conditions were not exactly the sort of conditions one would choose if the laws of nature had asked politely for better arrangements. On Principe, cloud was a serious problem. Eddington and his colleagues spent the morning under discouraging skies, uncertain whether the crucial moments would yield anything useful at all. One gets the impression, reading about such expeditions, that science, at its most dramatic, often involves standing about outdoors hoping the weather will develop character in a very specific direction. Not enough to be clear and sunny, of course, because then the eclipse observation becomes impossible. Not enough to be clouded over either. The heavens must be moody but cooperative. During totality, Eddington managed to obtain a number of plates despite the clouds, though not with the sort of effortless abundance one imagines in a triumphal retelling. The Sobral team, meanwhile, had better weather, but their work was not without complications. One of the instruments produced plates that later turned out to be problematic, possibly because of focus changes caused by temperature effects. Another instrument performed better. Already one can see how close the whole thing came to becoming an infuriating anecdote about great theory and rotten luck. After the observations came the more patient drama, which is often the real drama in science. The plates had to be measured, compared, interpreted, and argued over. This is where the neat public myth of instant revelation begins to blur into the more honest picture of analysis. The apparent shifts in the stars' positions had to be extracted from imperfect data. Different plates had different quality. Different instruments gave different levels of confidence. The outcome was not a thunderbolt from heaven. It was a careful weighing of evidence. What emerged from that weighing was that the better data supported Einstein's prediction, rather than the smaller deflection expected from a simpler Newtonian-style treatment. This was the crucial point. The starlight appeared to be bent by the amount general relativity demanded. The result was announced later that year in London, and it caused a sensation. Einstein, who had already transformed theoretical physics, suddenly became a public figure of almost mythical status. Newspapers announced that Newton had been overthrown. The idea that space itself could be curved seized the imagination far beyond scientific circles. It was one of those rare moments when an abstract physical theory stepped onto the front page and refused to leave quietly. There is a temptation, when telling this story, to frame the eclipse as a clean duel between Newton and Einstein, with one glorious observation and the whole matter settled by tea time. Real science is never quite that theatrical. Newton was not discarded. His theory remained astonishingly accurate in most ordinary circumstances and still does. What happened was subtler and more interesting. General relativity showed itself capable of handling situations where Newtonian gravity did not fully suffice. The eclipse did not erase the older theory. It revealed its limits and confirmed the need for a deeper one. There is also a temptation, especially among those who like their historical stories polished, to imagine the eclipse result as beyond dispute from the very beginning. That, too, is not quite right. Historians and scientists have revisited the details many times. They have examined the data, the judgments made about which plates to trust, the interpretation of the results, and the possibility of bias. That is not a scandal. That is what serious thought does. The important point is that later tests of general relativity, made with far more precise methods and much better instruments, have strongly confirmed the bending of light and the broader theory. The eclipse expedition remains historically important not because it was the final word forever, but because it was the first great public observational triumph of Einstein's gravitational vision. And what a vision it was! Think for a moment about what the eclipse result actually meant. It meant that a distant star, minding its own business at an immense remove from Earth, could have the path of its light altered merely because that light passed near the sun on its way to us. It meant the sky was not a neutral theatre of distant points, but a place where geometry could subtly reshape appearance. It meant that seeing was no longer just a matter of line of sight in the simple everyday sense. The line itself belonged to a spacetime whose shape mass could alter. That is a very large conceptual reward for a very small shift on a photographic plate. It also gave the public a rare and oddly charming picture of how science works at its best. Here was a theory born in deep abstraction, built from mathematics and thought experiments, predicting something so strange that many people found it almost absurd. And here were astronomers carrying heavy equipment to distant locations to wait for a shadow to cross the Earth, so that the stars behind the sun could be photographed for a few minutes. There is something endearingly excessive about that. Human beings will travel across oceans to measure a tiny angle in the sky in order to decide whether space is curved. That is not practical in the narrow sense. It is grandly, gloriously impractical in the service of truth. The eclipse also mattered because it gave the idea of bent light a concrete image. Before the observation, one could say that general relativity predicted the deflection of light, and that would sound interesting to some people and faintly bothersome to others. After the eclipse, one could say that stars near the sun's edge appeared displaced exactly because their light had not followed the route flat space would have provided. That is easier to picture. A star field had shifted. The sky itself had betrayed the geometry. The theory was no longer merely a bold claim about gravity. It had touched observation. From there, the road opens into a broader and even more remarkable territory. Once astronomers accepted that mass could alter the path of light, the universe became full of new possibilities. If the sun can bend starlight a little, what can a galaxy do? What can a cluster of galaxies do? What happens when the alignment is just right? Could gravity act as a lens, magnifying distant objects, creating arcs, splitting one source into many images? The eclipse did not answer all those questions immediately, but it made them feel real in a new way. It took the idea of gravitational light bending from theory into observed fact, and once fact is in place, imagination in science becomes far more dangerous in the best possible sense. Still, there is something worth pausing over in the human side of the event. The eclipse was not only a scientific test, it became a cultural turning point. Einstein emerged as the symbol of the new physics, the brilliant figure whose ideas had bent not only starlight, but the old confidence in common sense itself. The newspapers loved the drama of it. The notion that time and space were no longer fixed, that gravity was geometry, that Newton's great system had been surpassed in some domain. All of this was irresistible. One can hardly blame them. It is not every year that the cosmos provides a story in which a total eclipse helps rewrite reality. But beneath the headlines was the slower truth that makes science trustworthy. The eclipse mattered because it was a measurement, not because it was a spectacle. The spectacle helped the world notice. The measurement did the work. Plates were taken, positions were compared, errors were debated, confidence was earned. The public likes revelation. Science prefers repeated agreement with nature. In this case, happily, the two met long enough for history to remember. There is also a gentle irony in the fact that the test depended on the sun, because the sun had long been the great organizer of the visible sky. It governs day and night in the simplest human sense. It hides the stars during daylight. It warms the earth and structures time in ways ancient civilizations understood, long before relativity entered the conversation. And here, in the 20th century, the sun becomes the very object whose gravity helps reveal that space is curved and that light itself does not travel quite as naively as we once supposed. The old centre of daily experience becomes part of a new cosmic lesson. One might even say that the eclipse gave the sky a brief honesty impossible under ordinary glare. With the sun's disk hidden, the stars nearby could announce that their light had been nudged from the straight road. The evidence was always there, but only in that temporary arrangement could humans see it clearly enough. There is something almost moral in that, though perhaps that is pressing the moment too far. Still, nature does seem fond of requiring patience, timing, and a certain willingness to wait for the right shadow. The result also taught astronomers to trust light in a more complicated way. Light remained the great messenger, but it was now known to be a messenger whose route could be altered by gravity. That is not a flaw. It is an opportunity. If the route is altered lawfully, then the alteration itself becomes a source of information. One no longer sees bent light merely as an obstacle to be corrected. It becomes a tool. By studying how the path changed, one can infer the mass that changed it. In that sense, the eclipse did more than confirm general relativity. It quietly laid the foundation for an entire way of reading the universe. And perhaps that is the most elegant part of the whole story. The original puzzle was that light has no mass, so why should gravity affect it at all? The eclipse answer was not some hidden clause saying that under special circumstances light temporarily counts as heavy enough. The answer was far better. Gravity is not fundamentally a pull on masses alone. It is the shaping of space-time, and light follows that shape. During the eclipse, the stars did not misbehave. They told the truth about the road. Once that truth had been glimpsed, even imperfectly, it became impossible to look at large masses in the cosmos in quite the same way again. The sun had shown what a star could do. The next question, almost inevitably, was what larger structures might do with the same rule. If one star can shift the apparent positions of other stars, then a galaxy might do more. A cluster might do something more dramatic still. And the night sky, which had already become stranger by proving Einstein right, was about to become even stranger when astronomers realized that gravity could act not only as a test of theory, but as a lens for the universe itself. Once the eclipse had shown that starlight really could be bent by gravity, the idea stopped being a curious prediction and started becoming a method. That is often how science advances. A thing first appears as a test, a very narrow and careful question asked under special conditions. Then, once the answer is accepted, the same phenomenon opens outward and reveals itself as something much larger. What had seemed like a delicate oddity turns out to be a general feature of reality with uses no one could fully appreciate at the beginning. The bending of light followed exactly that path. At first, it was about whether Einstein had been right. Soon afterward, it became clear that the universe itself was full of situations where gravity was quietly redirecting light on a grand scale, and that those distortions were not merely tolerable complications, but extraordinary sources of information. This is where the idea of lensing comes in, and it's one of the most satisfying names in all of astronomy, because it manages to be both familiar and surprising at once. We know what an ordinary lens does. A glass lens bends light because light changes speed when it passes through material, and the shape of the lens redirects the paths of the rays. Put such a lens in front of your eye, or in a telescope, or in a camera, and the world looks different. Things can be magnified, focused, sharpened, distorted, brought near, or sent wandering into a blur depending on how competently the lens has been made and whether it has recently been dropped. That basic optical intuition gives us a way into gravitational lensing, though the mechanism is deeper. A gravitational lens does not rely on glass or crystal or polished surfaces. It relies on mass-curving spacetime so that light from a more distant source follows altered paths on its way to us. At first, that may sound like a metaphor stretched slightly beyond its comfort. A lens made of gravity sounds suspiciously like a phrase someone invented because they wanted a dramatic title for a lecture. But it is a very real thing. If a massive object lies between a distant source of light and an observer, the geometry around that mass can redirect the light enough to change the appearance of the source. Sometimes the source is shifted. Sometimes it is stretched into an arc. Sometimes it appears brighter than it otherwise would. Sometimes it is split into more than one image, so that one distant object seems to appear in several places at once. The universe, without asking whether we are ready, turns mass into optics. There is something wonderfully economical about that. Nature does not bother building separate systems when one structure will do. The same gravity that shapes the motion of planets and the paths of falling bodies also shapes the path of light. And once enough mass is involved, the effect can become not just measurable, but visually striking. Astronomers began to realize that the cosmos was not merely populated by stars and galaxies. It was also filled with gravitational arrangements capable of bending the appearance of whatever lay behind them. To understand how this works, imagine a very distant galaxy sending light outward in all directions. Some of that light travels toward us. If there is nothing particularly massive in the way, then the route remains close enough to what we would call straight that we simply see the galaxy, where we expect to see it. But suppose another galaxy, or better still a whole cluster of galaxies, lies between us and that more distant source. Now the light from the background galaxy enters a region where space-time is significantly curved. It can take paths around the intervening mass and still reach us, because more than one route may be available, and because the geometry can focus or stretch the arriving light, the background object may no longer appear as a neat single image. It may appear as a pair of images, or several, or as a long curved arc, or in especially symmetric alignments as a nearly complete ring. That ring is one of the most beautiful consequences of gravitational lensing, and it has a pleasingly dignified name. It is often called an Einstein ring. The name sounds almost too tidy, as though the universe had a good sense of branding, but the effect itself is quite direct. If the distant source, the intervening mass, and the observer line up almost perfectly, the bent light can arrive from many directions around the lensing object, forming a circle or partial circle of light. What was originally one source becomes a luminous ring, not because the source itself has become ring-shaped, but because the path structure around the lens is symmetric enough to wrap the image around the intervening mass. This is one of those moments in astronomy where the sky seems to be doing something ornamental even though the explanation is pure geometry. The ring is not decoration, it is a map of curved paths. Yet there is no denying that many such lensing images are extraordinarily beautiful. Long blue arcs curling around reddish galaxy clusters, duplicated points of light arrayed like careful punctuation marks, nearly complete circles glowing around massive foreground galaxies. These are not just scientific data in any cold sense. They are the visible handwriting of gravity acting on light. What makes lensing so valuable is that it allows mass to reveal itself even when the mass is not particularly bright. In ordinary life, seeing and weighing feel almost like separate activities. We look at something to know where it is, and we lift it, or watch how it moves to know how heavy it might be. Astronomy does not have that luxury. It cannot put galaxies on scales. Instead, it must infer mass from effects. Gravitational lensing is one of the best such effects because it depends on the curvature caused by mass regardless of whether that mass emits much light. If a galaxy cluster bends the light of background objects, then the pattern of the bending tells astronomers about the cluster's mass distribution. And often, rather inconveniently for simple visual assumptions, there turns out to be far more mass present than the glowing matter alone would suggest. This is one reason lensing became such a powerful tool in the study of dark matter. Dark matter remains one of the great mysteries of modern cosmology. It does not shine like ordinary matter. It does not announce itself with warmth or visible structure in the ways stars and gas do. Yet its gravitational influence appears again and again in the behaviour of galaxies and clusters. Lensing gives astronomers a way to map where that hidden mass must be. By studying how background galaxies are distorted, they can infer the gravitational landscape created by the foreground mass, including the invisible portion. In effect, light from far away is used to sketch the shape of matter we cannot directly see. That is a remarkable thing. It means the universe can be used against itself, in the nicest possible sense. A distant galaxy provides the light. An intervening cluster provides the lens. The observer measures the distortion, and from that distortion hidden mass is inferred. One cosmic object reveals another by altering the path of a third. This is not the sort of arrangement anyone designing the universe for convenience would have chosen, but it is a marvellous arrangement for discovery. There are different regimes of lensing, and it is worth wandering through them slowly because each tells a slightly different story. The most dramatic form is often called strong lensing. This is what happens when the alignment is favourable, and the intervening mass is large enough to produce obvious distortions like arcs, multiple images, or rings. Strong lensing is the sort of thing that can look astonishing even in a single image. A background galaxy appears smeared into a bright curved ribbon. A quasar appears in 4 separate positions around a foreground lensing galaxy, like a celestial joke about duplication. These are the lensing events that most clearly announce themselves to both astronomers and anyone else lucky enough to see the photographs. Then there is weak lensing, which sounds less exciting but is in some ways even more subtle and powerful. In weak lensing, the distortions are not dramatic enough to shout from a single object. A background galaxy is stretched only a little. Another nearby one is also stretched. Individually, each distortion could be dismissed as ordinary variation in shape. Galaxies are not all neatly symmetrical to begin with, and the universe is not in the habit of labelling them helpfully. But when vast numbers of galaxies are studied statistically, patterns emerge. Whole regions of sky show slight coherent distortions caused by intervening mass. By analysing these patterns across many background sources, astronomers can reconstruct the distribution of matter, both visible and dark, on large scales. weak lensing is a kind of cosmic whisper. It does not produce theatrical rings. It produces subtle biases that, when measured carefully, reveal the scaffolding of mass across the universe. There is also microlensing, which is a delightfully modest-sounding term for an effect that can be very useful indeed. In microlensing, the lensing mass is not a galaxy or cluster, but a smaller object such as a star, a compact remnant, or perhaps a planet. The images produced are usually too close together to be resolved directly, so astronomers do not see neat, separated points. Instead, what they observe is a temporary brightening of the background source as the lensing object passes in front. The geometry briefly focuses more light toward us, and the source appears to brighten and then fade in a characteristic way. Microlensing has been used to detect objects that emit very little light themselves, and it has even played a role in the discovery of exoplanets. A star or planet can betray its presence not by shining, but by the way its gravity briefly magnifies the light of something behind it. Again and again, lensing turns the apparent weakness of observation at great distance into a strength. We cannot touch these objects. Very well, then we will let them distort one another and read the result. It is difficult not to admire the ingenuity involved, though one should also credit the universe for providing the opportunities in the first place. There is another beautifully strange consequence of multiple light paths in strong lensing. If the same background source is seen in more than one image, the light reaching us by those different routes may have travelled different distances and passed through different gravitational conditions. That means the arrival times can differ. If the source varies in brightness, as some quasars do, the changes may appear in one lensed image and then later in another. In other words, lensing can create a sort of delay between copies of the same distant object. The universe not only duplicates the image but staggers the delivery. Astronomers can use these time delays to learn about the geometry of the lensing system and even about cosmic expansion. Once again, what sounds like a nuisance in ordinary optics becomes a source of precision when handled carefully enough. It is also worth appreciating how lensing changed the practical reach of astronomy. Massive galaxy clusters can act as natural telescopes, magnifying the faint light of even more distant galaxies behind them. This means that some of the most remote objects we have studied in the universe have been made more visible because foreground mass happened to lie in the right place to bend and amplify their light. Human beings build telescopes with great effort and expense, polishing mirrors, cooling instruments, launching observatories into space, all of which is admirable and necessary. But meanwhile, the universe has been constructing its own lenses out of mass for billions of years, and occasionally those lenses align just well enough for us to benefit. It is as though the cosmos, while generally indifferent, sometimes leaves a magnifying glass lying about in exactly the right place. This has allowed astronomers to glimpse extremely faint and distant galaxies that might otherwise have remained beyond reach. A lensed galaxy can appear stretched and brightened, making features observable that would have been too dim without the extra help from gravitational magnification. There is something quietly satisfying in that arrangement. The very mass that obscures and distorts also reveals and enlarges. Gravity, which once seemed merely to complicate the route of light, becomes an accomplice in seeing farther. Of course, lensing is not always convenient. Distortion can make interpretation more difficult. If a galaxy is stretched into an arc, one must work backward through the lensing geometry to infer what the source actually looks like. This requires modelling, patience, and a willingness to trust both the data and the theory at the same time. But astronomy has never had the luxury of refusing complicated gifts. The sky offers information in the form it pleases, and scientists learn to read it. There is a deeper philosophical charm in all this as well. Lensing means that the universe is not visually honest in the naive sense, but it is lawful. Things are not always where they appear to be in a simple line of sight picture. Background sources may appear split, shifted, magnified, or curved. Yet these changes are not arbitrary illusions. They are the understandable consequences of spacetime geometry. This matters because it reminds us that appearance in astronomy is always already interpretation. The light that reaches us has travelled, and the journey matters. A lensed image is not false. It is informative in a richer way than an unlensed one. The more one thinks about lensing, the more it seems less like a special effect and more like a natural language of the universe. Massive objects shape the paths of light. Background sources announce those shaped paths by appearing altered. Observers decode the alteration and infer the mass. It is an elegant chain. One begins with the old puzzle. How can gravity affect massless light? And one ends with entire maps of hidden matter drawn from the way galaxies behind it are stretched across the sky. One can even say that lensing teaches humility about what it means to look. We often imagine seeing as direct, but in the cosmos, seeing is routed. Every image is the endpoint of a journey through geometry, and sometimes that geometry is curved enough to leave obvious traces. The sky is not a flat display board of distant lights. It is a layered three-dimensional, and indeed four-dimensional structure in which the between matters as much as the objects themselves. The root is part of the reality. All of this emerged from the same core idea first confirmed in miniature by the bending of starlight near the sun. Once it was accepted that gravity could redirect light, the implications spread outward through astronomy like dawn moving over a landscape. A star could lens a star a little. A galaxy could lens a galaxy more. A cluster could turn the far universe into arcs and rings. Invisible mass could announce itself by distortions alone. Time delays could be measured between duplicate images. Distant galaxies could be magnified by foreground gravity. The cosmos had become not just a place full of light, but a place full of light shaped by gravity in ways that could be read. And yet, as dramatic as lensing can be, it still belongs to the gentler end of what gravity can do to light. The path is bent, perhaps strongly, perhaps even enough to make circles and multiple images, but the light still escapes and reaches us. It is redirected rather than destroyed. That naturally leads the mind toward more extreme situations. If a galaxy cluster can stretch a background source into a long bright arc, what happens near an object whose gravity is so severe that the available paths for light narrow far more drastically? What happens when mass is packed densely enough that bending becomes trapping, and the route of light is altered not just by a little, or even by a lot, but in the most absolute way the theory allows? That question, waiting just beyond the luminous arcs and graceful rings, is where the road begins to darken toward black holes and the stranger fate of light near them. By the time gravity has stretched galaxies into arcs and turned distant sources into rings, the mind is already half prepared for something more severe. Once you accept that mass can bend light, it becomes hard not to ask where that bending finally leads. Is there a limit to how far the path can be redirected? Can light be bent around an object so strongly that it circles it? Can it be trapped? And if light, the great messenger of the cosmos, the one thing we rely on to reveal almost everything else, can be prevented from escaping, what sort of object would do that? These are the questions that gather around black holes, and they gather there for good reason, because black holes are where the relationship between gravity and light stops being merely elegant and starts becoming extreme. There is a temptation, whenever black holes enter the conversation, to let the tone become dramatic very quickly. One can hardly blame anyone for that. The phrase itself sounds as though it was invented by a novelist on a day when subtlety had gone on holiday. Black holes have become the celebrities of modern astrophysics, and like many celebrities, they are often discussed with more excitement than care. They are described as cosmic monsters, bottomless drains, impossible abysses, celestial vacuum cleaners with an appetite for everything in reach. Some of that language is vivid, and some of it is not entirely wrong, but much of it gives the wrong picture. Black holes are not magic holes bored into the universe. They are not places where the laws of physics go on strike and wander away. They are objects predicted by general relativity, when enough mass is compressed into a small enough region that the curvature of spacetime becomes extraordinarily strong. And the most important thing about them, for our purposes tonight, is what they do to light. To understand why black holes matter so much here, it helps to begin with a simpler question. What does it mean for light to escape from a gravitational field at all? We're used to thinking about massive objects needing enough speed to escape gravity. Throw a ball upward too gently and it falls back. Launch a spacecraft fast enough and it does not. That idea makes easy sense for matter. But light does not gradually try harder the way a rocket does. Light always moves at the same speed in empty space. So if gravity affects its path, the issue cannot be whether it will simply move faster and outrun the pull. The issue is whether the geometry of space-time still provides a path leading outward. Near ordinary stars and planets, it does. Light leaving the surface of the sun is affected by the sun's gravity, but it escapes. Light from Earth rises into space. Light bent near galaxies continues on its journey. Black holes are what happen when the curvature becomes so severe that beyond a certain boundary, no outward path remains available for light at all. That boundary is called the event horizon, and there is something profoundly unsettling about it, precisely because it is not a solid surface in the everyday sense. If you think of a wall, a shell, or a crust, you are already imagining too much furniture. The event horizon is not a material barrier one might tap with a knuckle or decorate badly. It is a boundary in space-time, a dividing line between regions where escape remains possible and regions where it does not. Once light crosses that boundary inward, there is no route back out to the wider universe. The future, as defined by the geometry there, points inward. That is the key idea. The event horizon is not a place where light gets tired or forgets its duties. It is a place where the structure of space-time itself has become such that all possible forward paths lead deeper in. That is a very strange thought, and it deserves to be approached slowly because it is easy to turn it into the wrong kind of horror. People often imagine a black hole as a thing with immense suction, as though it sits in space greedily pulling everything toward it with some special added violence. But a black hole at a given distance does not exert some mystical extra gravity compared with any other object of the same mass. If the sun were somehow replaced by a black hole of equal mass, the Earth would not suddenly be slurped inward like a pea near an overenthusiastic child. It would continue orbiting more or less as before, though admittedly the lighting conditions would become unhelpful rather quickly. What makes a black hole special is not that its gravity is magically stronger at large distances. It is that the mass is concentrated so densely that very close to it the curvature becomes extreme enough to produce an event horizon. So what happens to light near such an object? Quite a lot, and in stages. Light passing at a safe enough distance is merely bent, perhaps strongly, but it can still continue on and escape. This is gravitational lensing in a more intense register. The black hole can distort the appearance of background stars or gas around it. It can produce rings, multiple images, and all the strange visual effects one would expect from an object whose space-time geometry is severe. Move closer, however, and the bending grows stronger. There exists a region outside the event horizon where light can, under the right conditions, orbit the black hole. This is often called the photon sphere. Even the name has a certain austere grandeur, though one must not let it sound too cozy. This is not a calm, traffic circle for well-behaved beams. It is a region where the geometry allows light to travel around the black hole in unstable circular paths. Unstable is the important word. A tiny disturbance inward and the light falls in. A tiny disturbance outward and it escapes, though perhaps only after looping around in a most undignified way. The existence of such a region tells you a great deal about how distorted the geometry has become. Light, which ordinarily traces out the structure of space-time with quiet efficiency, can be bent around and around. In principle, photons skimming near a black hole can circle it one or more times before escaping toward a distant observer. This leads to some extraordinarily strange optical possibilities. An observer near a black hole, or even far away looking toward one, would not see the background universe in any ordinary way. Light from stars behind the black hole could be wrapped, duplicated, compressed into rings, bent into halos, or sent in looping paths that create multiple apparent images. The universe becomes optically baroque. This is one of those rare places where the actual physics sounds almost more fanciful than the fiction. And yet it is not fantasy. It is geometry doing exactly what general relativity says it ought to do when the curvature becomes extreme. A black hole is not simply dark because it emits no light of its own in the ordinary sense. It is dark because once light has crossed the event horizon inward, the larger universe cannot receive it back. The blackness is not a colour, it is the absence of return. There is another effect worth lingering on here, because it adds a melancholy sort of subtlety to the story. Like climbing away from a strong gravitational field is redshifted. That means its wavelength is stretched and its energy, from the perspective of a distant observer, is reduced. Near a black hole, this effect becomes more and more pronounced. Light emitted from matter very close to the event horizon can still escape if it starts outside the horizon, but it does so under increasing strain, arriving weaker and more reddened as the gravitational field deepens. To a distant observer, processes occurring near the horizon can appear slowed and dimmed. Signals stretch out. Time itself, as described from afar, seems to drag. This is not because the light is lazily taking its time, but because gravity has become entangled with the structure of time as well as space. This leads to one of the strangest apparent contradictions in the black hole story. If you imagine an object falling toward a black hole, your own description of what happens depends on where you are. If you're falling with the object, crossing the horizon might not feel like a dramatic local event at all, at least for a sufficiently large black hole where tidal forces at the horizon are not yet catastrophic. But to a distant observer, the infalling object appears to slow, dim, and asymptotically fade as it approaches the horizon. The light it sends out is stretched and weakened, and the signals take longer and longer to arrive. It is as though the object never quite finishes the crossing from that distant perspective, even though in its own journey the crossing can happen in finite time. Black holes are full of such perspectival oddities, not because reality has become inconsistent, but because space-time near them is no longer playing by the habits of ordinary intuition. And what of the light emitted by material around a black hole, rather than by things falling directly in? That too is part of the story, because black holes are often most visible not by what escapes from within, but by what happens just outside. Gas and dust spiralling toward a black hole can form an accretion disk, a flattened structure of intensely heated matter. Friction, compression, and magnetic processes in that disk can make it glow with extraordinary brightness, sometimes in visible light, sometimes in X-rays and other forms of radiation. So black holes, despite their name, can be associated with some of the brightest regions in the universe. The darkness lies in the trapped interior and the horizon itself. The drama outside can be incandescent. This is another place where the ordinary imagination has to be gently corrected. A black hole is not merely a black ball against a neat starry background. If there is matter around it, the scene can be violent, luminous, and distorted in spectacular ways. The glowing disk may appear warped by gravitational lensing. Light from the far side of the disk can be bent over and around the black hole, so that it becomes visible from above, producing an image far stranger than any simple flat ring. The black hole can cast a kind of shadow against that luminous background, not because it is a surface blocking light like a walnut on a lamp, but because the space-time near it redirects and traps light in such a way that a dark region appears in the observed image. This became more than theory in a very public way when humanity first obtained images of the shadow of a black hole using the Event Horizon telescope. What was seen was not the event horizon itself in a direct simple sense, but the silhouette produced by the trapping and bending of light around the black hole, set against glowing material near it. That image, fuzzy and ringed and profoundly moving for many people, was one of the great modern confirmations that these bizarre objects are not just mathematical curiosities. They are real astronomical entities shaping the light around them in exactly the sort of ways general relativity prepared us to expect. Still, the event horizon remains the emotional centre of the black hole story because it marks the point where the fate of light changes categorically. Outside it, light may be bent, delayed, redshifted, forced into loops, or thrown into strange visual patterns, but some outward futures remain. Inside it, that possibility disappears, and this is why black holes matter so much to our original question. If gravity-bending light already forced us to abandon the idea that gravity acts only on mass in the old sense, black holes drive the lesson home with terrifying clarity. Here is an object whose gravity does not merely alter the path of light. It shapes space-time so completely that even light cannot find a path back out once too far in. There is something almost philosophical in the way black holes redefine escape. In ordinary life, escape suggests effort. One climbs, runs, swims, or launches. One simply needs enough power or speed. But near a black hole, the issue is not strength. The issue is geometry. If all future directed paths lead inward, then escape is not difficult, it is undefined. The road out no longer exists. That is a deeper and stranger kind of imprisonment than any force-based picture can easily convey. And yet, as severe as all this sounds, black holes are not merely destructive curiosities, they're also laboratories for understanding gravity at its most extreme. They reveal how light behaves in strong curvature. They test general relativity under demanding conditions. They power some of the most energetic phenomena in the universe through their surrounding disks and jets. They influence the evolution of galaxies. They stand at the edge of one of the biggest unfinished conversations in physics. Because when quantum theory is brought into contact with black holes, new puzzles emerge about information, radiation, and the deepest nature of spacetime itself. That quantum story is a large and troublesome one, and perhaps tonight we need not follow it all the way into its more argumentative corners. It is enough to note that black holes are not the end of thought. They are where thought becomes more urgent. The fact that light can be trapped, that horizons can exist, that time and observation behave so strangely near them, all of this tells us that gravity is not merely a background convenience. It is one of the great sculptors of physical reality. There is also a more gentle lesson hidden in the black hole story despite all the drama. We began with a puzzle about light having no mass and gravity bending it anyway. At first, that sounds like a contradiction in the rule. Then, as the story unfolds, the contradiction dissolves and becomes a clue. Light bends because gravity is geometry. Black holes are simply where that geometry becomes so severe that the full implications can no longer be ignored. They are the place where the old everyday language of pull finally gives way entirely to the deeper language of paths and boundaries and curved futures. If you picture a beam of light passing near a star, you have the mild version of the story. If you picture it stretched into an arc by a galaxy cluster, you have the grand version. If you picture it circling, reddening, and finally crossing a horizon beyond which no return route remains, you have the extreme version. But it is all one story. The fate of light is written by the geometry through which it moves. And once you begin thinking in these terms, another question starts to press gently at the edges. We have spoken about what we see, how light bends, how it escapes or does not, how distant observers describe what happens near strong gravity. But what does it mean, in the language of the theory, to speak of light's own journey? Does light experience time? What is the path like from the perspective of the traveller itself, if that is even a meaningful thing to ask? That question is subtle and a little dangerous, because it touches the limits of ordinary language as much as the limits of intuition, and it takes us from the visible drama of black holes toward the stranger issue of what, if anything, can be said about light on the journey itself. By the time we reach this point, the temptation is almost irresistible. We have watched light bend near stars, slip around galaxies, form arcs and rings, skim the edge of black holes, and vanish beyond horizons where no return path exists. we have spoken about how gravity shapes the route and how observers, whether nearby or distant, describe what happens along the way. So naturally the mind asks one more question, perhaps the most intimate one of all. What is it like for the light itself? What does light experience on the journey? It is a very human question, and therefore both helpful and dangerous. Helpful because it tries to bring the strange abstractions of physics into a form we can emotionally grasp. Dangerous because light is not a tiny person in a bright coat keeping a travel diary. It does not have a viewpoint in the ordinary sense. It does not get bored crossing intergalactic space. It does not feel alarmed near a black hole. It does not complain that the route was longer than expected and the service rather poor. Yet the question remains worth asking, provided we immediately treat it with care, because hidden inside it is a real issue about time, motion, and the limits of what relativity allows us to say. In ordinary life, whenever we ask what a journey is like, we mean something structured by time. How long did it take? What happened first? What changed along the way? What did the traveller see, feel, or measure between departure and arrival? All of those questions assume the traveller has a frame of reference in which it can be at rest with itself and watch the world go by. That assumption works very well for trains, bicycles, meteors and people. It even works for astronauts, though the paperwork is often more ambitious. But light is different in a very profound way. Light does not have a rest frame in the ordinary relativistic sense. You cannot move alongside a beam of light and declare yourself stationary with respect to it in a physically meaningful way. The whole structure of special relativity forbids that. That point matters more than it may first seem. When we talk about what a moving object experiences, we usually imagine sitting in its frame and measuring time along its path. A person carries a watch. The watch ticks. Whatever happens, happens in that measured sequence. If the person moves very fast relative to someone else, the two may disagree about durations and simultaneity, but each still has a perfectly valid local time along their own journey. This is called proper time, though one need not dwell on the phrase too technically. It is the time actually experienced along the path of the traveller. A person falling toward a black hole has one, a satellite has one, even a muon racing through the atmosphere has one. Light does not in the same way. Along the path of light in relativity, the interval that would correspond to experienced elapsed time is, in the language of the theory, not like that of ordinary travellers. This is where people often hear a popular statement and become understandably intrigued. They hear that for light, no time passes between emission and absorption. Then they imagine the photon somehow leaving a distant star and arriving in your eye with no interval at all, as though the whole journey across millions of years of cosmic history were, from light's own perspective, instantaneous. It is an arresting thought. It has the slightly intoxicating flavour of something both scientific and philosophical, and like many such statements it needs to be handled gently or it begins to mislead. The problem is not that the statement points in entirely the wrong direction. The problem is that the phrase from a light's own perspective sounds more legitimate than it really is. Strictly speaking, relativity does not allow a rest frame for light, so speaking of a full physical perspective belonging to a photon is already stretching the language. We are borrowing intuition from ordinary objects and trying to lay it on something that resists it. That is why the quotation marks around experiences are doing so much work tonight. They are there to remind us that the question is useful only if we do not take it too literally. Still, something deep is being gestured toward. The mathematical structure of relativity tells us that light-like paths are different from the paths of slower moving objects. For ordinary matter, there is a meaningful distinction between here and later along the journey as measured by the traveller. For light, that familiar measure collapses in a way that no ordinary experience prepares us for. So while we cannot honestly give light a cosy first-person narrative, we can say that the route of light through space-time is not accompanied by elapsed proper time in the ordinary sense. That is one reason light occupies such a special place in the theory. It sits at the limit. It connects events without itself being an ordinary time-keeping participant. If that sounds abstract, it may help to approach it from the observer side first. Imagine a photon emitted from a distant galaxy and eventually absorbed by a telescope on Earth. For us, the journey can take millions or billions of years depending on the source. We can talk about that duration meaningfully because we exist in frames where clocks tick, galaxies evolve, stars are born and die, civilizations worry about whether they left the oven on, and so on. The photon serves as the messenger linking the distant event and the detection event. But asking how many years passed for the photon itself is not like asking how many years passed for a traveller on a ship. The framework that would let us answer that in the usual way is not available. This is one of those places where physics teaches humility about language. Our grammar wants every journey to have a traveller, and every traveller to have an experience of the trip. Light refuses that story. It makes more sense to say that emission and absorption are linked by a light-like path than to imagine a tiny witness accompanying the route with a functioning wristwatch and a set of opinions. And yet, if we are careful, the temptation to personify light still tells us something useful. It tells us that light occupies a peculiar status in the structure of space-time. It is not merely another moving thing. It marks the fastest possible transmission of information in vacuum. It defines causal connections of a certain kind. It sits on the boundary between what can influence what in relativistic space-time. In a deep sense, light helps define the architecture of cause and effect. So while light does not have an ordinary experience, its paths are among the most important in the whole theory. This becomes especially interesting when gravity enters the story, because gravity changes those paths without ever needing light to have mass. Near a massive object, the path of light is bent. Near a black hole, it may loop or fail to escape. Light climbing out of a gravitational well is redshifted. Light passing through an expanding universe is stretched as space itself changes. In all these cases, the important question is not what the photon feels, but what the geometry does to the relation between emission and detection. The language of experience is tempting, but the language of structure is safer. Still, one can understand why people keep asking the question. There is something almost haunting about the idea that the light from a star can travel for ages and yet not fit cleanly into our ordinary notion of duration. We are creatures of time. We wake, age, remember, anticipate, and count. To us, every journey is steeped in sequence. To encounter an entity that links moments across the universe, while not admitting the same style of elapsed time along its own path, is deeply strange. It hints that time in physics is not one universal substance poured evenly over everything, but something tied to motion, geometry, and the kind of path involved. This is one of the great gifts of relativity. It takes words we thought we understood: time, distance, simultaneity, journey, and teaches us that they depend on structure. Two observers moving differently can disagree on the timing of events, and both be right in their own frames. A clock near strong gravity can genuinely tick more slowly than one farther away. And light, travelling at the universal speed in vacuum, occupies a limiting case that ordinary intuition can only circle around rather than inhabit. Another common way people try to picture this is by imagining that light somehow sees the universe compressed along its direction of travel. Again, one must be careful. This idea grows out of real relativistic effects such as length contraction, where distances measured in one frame differ from those measured in another moving frame. But because there is no valid rest frame for light, one cannot simply extend that reasoning all the way and declare a proper visual world from the photon's point of view. That is where the metaphor outruns the theory. Still, the reason such images appeal is clear. They are attempts to make sense of the special role light plays at the edge of what spacetime allows. And perhaps there is value in keeping that edge visible. Science does not always reward us with a fully picturable answer. Sometimes the most honest answer is that the question must be reframed. What does light experience on the journey becomes, in a more precise language, What kind of path in space-time connects the emission and absorption events, and what invariant or non-invariant quantities can observers assign to that path? That is less cosy, admittedly. It will not make many tea mugs or decorative posters, but it is closer to the truth. There is another part of the story that makes the question worthwhile. Even if light does not have an ordinary experience, different observers certainly experience the light differently depending on their motion and gravitational environment. A photon emitted from a distant source may be seen at one energy by one observer and another energy by someone moving differently. It may be blue shifted for one, red shifted for another. Its frequency, wavelength, and arrival pattern are not absolute in the naive sense. They depend on the relation between source and observer and on the geometry the light has traversed. So while the photon's own viewpoint is not a well-formed concept, the relational story surrounding the photon is rich and physically meaningful. Consider a simple example. Light climbing away from a massive star is red-shifted. The observer far away receives it at lower frequency than it had when emitted. Has the photon changed? In one sense, yes, the measured energy at detection differs from that at emission. In another sense, the real issue is the relation between the space-time geometry, the emitter, and the receiver. The light is the link. It is not carrying a private fixed label called true energy independent of all circumstances. What matters physically is how source and detector are related through the curved structure of space-time. Or think of the expansion of the universe. Light from distant galaxies arrives stretched, its wavelength increased by cosmic expansion. The familiar phrase is that the universe has red-shifted the light. Again, it is tempting to imagine the photon feeling itself pulled long like taffy over billions of years. That is charming, but not quite right. Better to say that as space-time expanded during the propagation of the light, the relation between emission and detection changed in a way that shows up as redshift. The photon is the messenger. The message bears the imprint of geometry and motion. This is why the concept of experience keeps wanting to sneak back in even when it should not. Journeys matter to us because they collect change. Something that leaves here and arrives there usually has a story written into it. With light, the story exists, but it is not internal in the way our human intuition expects. It is written into the relation between events, observers, and space-time. The photon's route matters immensely. The photon as a little narrating subject does not. There is a quiet elegance in that. Light becomes almost pure relation. It is how distant things become knowable to one another within the constraints of space-time. It links source and observer without itself fitting neatly into the same temporal categories that govern slower travellers. It marks the boundary of causality. It carries information, energy, and momentum. It reveals geometry through bending, redshifting, delay, and lensing. And yet if we ask it for a diary of the journey, relativity gently takes the notebook out of our hands. This is also one reason light feels so philosophically suggestive. It is both deeply physical and strangely resistant to ordinary picture thinking. We can measure it with exquisite accuracy. We can predict its behaviour. We can manipulate it in laboratories and decode it from the farthest reaches of the sky. But when we ask what it is like to be light, the answer is not merely difficult. It is not quite the kind of question the theory permits in the form we first imagined. That is not a failure of physics. It is a clue that some questions arrive wearing human clothes that do not fit the underlying reality. And perhaps that is fitting. After all, our whole journey through this topic began with a question that sounded simple in the language of common sense. If light has no mass, why does gravity bend it anyway? The answer turned out not to be a patch to the old intuition, but a redesign of the framework. Gravity is not merely a pull on heavy things. It is geometry. Light follows that geometry. Along the way, we discovered that light itself occupies a special status in the architecture of space-time. It is not just another traveller. It is the thing that sits at the edge of what motion and causality can mean. There is one more gentle point worth making, because it brings the story back toward the human scale without spoiling the science. Even though light does not have an ordinary experience of duration, we do. The photons reaching your eyes tonight may have come from a lamp a few feet away, from the moon after a short journey across space, or from stars whose light began long before you were born. For you, for me, for any creature living by clocks and memory, those durations matter. We inhabit the temporal richness that light connects. So when we talk about ancient starlight arriving now, we are speaking in a perfectly meaningful human and physical way. The fact that the photon itself does not have a standard little timeline is not a loss. It is simply a reminder that reality is built from relations more subtle than our first metaphors allow. And there is something quietly beautiful in that. The universe does not require every messenger to share our style of being in order to carry meaning to us. Light need not have a lived journey in our sense for its route to matter. It need not age as we do for it to bring us history. It need not possess a valid first-person frame for it to shape the entire structure of what can be known across space. In some ways, that makes light even more extraordinary, not less. It is not a diminished traveller because it lacks the ordinary terms of travel. It is a different kind of participant altogether. So when people say that no time passes for light, the most honest response is both yes and not quite. Yes, in the sense that the relativistic structure of a light-like path does not carry elapsed proper time the way ordinary matter does. Not quite, in the sense that speaking of light's own perspective too casually can smuggle in a rest frame that the theory does not allow. The truth sits between the catchy phrase and the careful mathematics, as it often does. And that, perhaps, is where the topic leaves us most fruitfully unsettled. Light bends though it has no mass. It can be delayed, redshifted, lensed, trapped, and stretched by the geometry of space-time. It carries news across the universe while itself resisting the ordinary language of a traveller's inner timeline. The more closely we look, the less it resembles the everyday objects our intuition was built to handle. Yet the less familiar it becomes, the more central it appears. Light is not merely something in the universe. It is one of the clearest ways the universe tells us what sort of place it is. Which brings us very gently toward the final question beneath all the others. If a massless beam can have its path rewritten by geometry, if the sky can misplace stars, if gravity can become optics and black holes can decide the fate of light itself, then perhaps the deeper lesson here is not only about light or gravity alone, but about how often reality turns out to be more relational, more structured, and more quietly astonishing than the first glance ever suggests. After all of this, after the stars nudged out of place, the eclipses, the arcs around distant galaxies, the shadowed edge of black holes, and the peculiar fact that light has no mass and yet still refuses to travel through gravity unchanged, it is worth asking what exactly we have learned. Not just in the technical sense, though there is plenty of that, but in the quieter sense. What is the lesson hidden inside this whole business of a bent beam? Why does this question linger in the mind long after the details have been sorted out? Why does it feel like more than a clever scientific trick? Part of the answer is that the question begins in a place that seems almost embarrassingly simple. Gravity pulls on things with mass. Light has no mass, therefore gravity should leave light alone. That sounds neat, tidy, and complete. It has the satisfying shape of common sense. You can almost hear the mind shutting the drawer and moving on to something else. But the universe does not always reward that kind of confidence. Sometimes the neatest thought is only neat because it has quietly ignored something deeper. In this case, what it ignored was the nature of gravity itself. The bent beam was the clue. It told us that gravity was not merely a force acting on heavy objects the way a hand pulls a rope or a magnet tugs a paperclip. It told us that the stage itself had been misdescribed. That is the first quiet lesson. The world is not always organised in the way our most immediate intuition prefers. That does not mean intuition is useless. Far from it. Intuition is often how inquiry begins. It gives us the first shape of a question. It helps us notice when something is odd. But intuition is local. It is built from dropped keys, thrown balls, roads, windows, weather, and the general business of surviving among medium-sized objects moving at modest speeds. It is not built for starlight passing near a star or for time itself shifting under gravity. When we forget that, we make the old mistake of assuming that the world must be simple in just the way our daily experience recommends. The bent beam reminds us to be more careful. It says that reality may be understandable without being obvious. That is an important distinction. Something can make sense once the right framework is in place, even if it looked impossible in the wrong one. Light bending under gravity is exactly like that. Under the old story, it seems contradictory. Under the deeper story, it becomes almost inevitable. Not because the universe changed its mind, but because we finally asked the question with better tools. And there is something quietly reassuring in that. The universe is not irrational. It is not making exceptions out of spite. The beam bends for a reason. The reason is not the first one we guessed, but it is still a reason that matters. It means nature remains lawful even when it surprises us. In fact, one of the most comforting things about physics is that the surprises are usually signs that the laws are deeper than we thought, not that the laws have vanished. The second lesson is about appearances. We like to think that seeing is direct. You look at a thing, and there it is. A lamp across the room, the moon above the trees, a star in the night sky. We treat light as a reliable courier of location. But this story has shown that light does not merely bring us images. It brings us images shaped by the root. A star can appear slightly displaced because its light passed near the sun. A distant galaxy can be stretched into an arc because a galaxy cluster lay between it and us. A black hole can carve a shadow out of glowing matter, not because it is a painted circle in space, but because the paths available to light around it have changed. In every case, appearance is tied to geometry. That is not a reason to distrust what we see. It is a reason to understand seeing more carefully. Vision in the universe is not a simple line from object to eye. It is a lawful relationship between source, path, and observer. Once you know that, the sky becomes richer. It stops being a flat display of distant lanterns and becomes something more intricate. Light arrives with history attached. It has crossed space, and sometimes curved space. The image before you is not false. It is the result of a journey. And if the journey has been bent, the bending itself becomes part of what can be known. This is one of the loveliest things about science. What begins as an obstacle becomes a tool. The bending of light first looks like a complication, something that gets in the way of a clean picture. But then it becomes one of the most powerful methods in astronomy. By studying distortions, we infer mass. By reading arcs and rings, we map galaxy clusters. By noticing weak systematic stretching across the sky, we trace dark matter. Gravity, which seems at first to be interfering with sight, turns out to be helping us see more than we otherwise could. A bent beam is not merely a deviation, it is evidence. That leads to another lesson, one perhaps more human than scientific, though still rooted in the science. The root matters. We are often very outcome-oriented creatures. We ask where something ended up and forget to ask how it got there. But in this whole story, the path is everything. The path of the light, the geometry of space-time, the history between emission and arrival. Even in daily life, though on a humbler scale, the route often matters more than we first admit. Two people can arrive at the same room by very different roads. Two ideas can produce the same answer by different reasoning, and the better reasoning matters. Two lives can look similar from a distance and carry completely different journeys underneath. A bent beam is, in its own calm, scientific way, an argument against shallow conclusions. You do not know enough just by seeing where something appears. You need to know what shaped the path. There is also the lesson Einstein forced upon gravity itself. For centuries, gravity was understood through a remarkably successful picture of pulls and masses. That picture still works brilliantly in many situations. But the bent beam revealed its limit. Gravity was not merely a hidden tug acting across emptiness. Space and time themselves were involved. This is one of the grand pattern changes in intellectual history. It is not just a new answer, it is a new way of asking. Instead of saying what force is pulling this thing, one asked what geometry is guiding its motion. Instead of saying light should be immune because it lacks mass, one asks what paths are available to light in a curved space-time. That shift matters beyond physics. Every so often, knowledge takes a step that is larger than a fact. It changes what counts as a sensible question. Once that happens, old puzzles lose their old form. If light bends because the road is curved, then the original contradiction dissolves. It no longer makes sense to demand that gravity behave only as a pull on heavy objects. The bent beam tells us we were describing the world in too narrow a language. And once the language broadens, the world becomes more coherent, not less. This is another quiet lesson. A better explanation often feels stranger at first and simpler later. We tend to assume simplicity should arrive immediately. If it is true, surely it ought to feel obvious on first hearing. But that is not how deep understanding usually works. Often the first encounter with a better framework feels awkward, almost rude. Curved space-time sounds more complicated than force. Gravity as geometry feels less intuitive than gravity as pulling. Yet after a while, the deeper picture begins to settle, and then oddly enough it starts to feel cleaner than the old one. The bent beam fits, the redshift fits, the lensing fits, the black hole fits. The old story has to keep making exceptions. The new one lets the pieces belong together. There is something satisfying about that kind of unity. Science is at its best when a single idea quietly explains many things at once. General relativity does that here. It tells us why planets move as they do, why clocks run differently in gravitational fields, why light bends, why lensing happens, why black holes can trap light, and why even the path of a massless beam still belongs to gravity's domain. One framework, many consequences. The bent beam is not an isolated wonder, it is part of a larger pattern. And patterns matter because they tell us whether we are merely collecting facts or actually understanding something. Anyone can memorize that starlight bends near the sun. Understanding begins when you see why that fact belongs with all the others. The real achievement is not the isolated answer, it is the arrangement. Then there is the matter of scale. We have spent this whole journey talking about stars, galaxies, clusters, and black holes, and it would be easy to leave the topic there, filed away under interesting things the universe does very far from the sofa. But the lesson hidden in a bent beam is not confined to remote objects. Relativity is not a distant myth only for astrophysicists with impressive hair and robust access to observatories. The geometry of space-time is woven into the world you live in. Satellites used for navigation have to account for relativistic effects or their timing drifts. The sun's mass really does bend light. The Earth's gravity really does affect clocks. The framework that explains the distant cosmos also reaches quietly into the ordinary technologies of life. I think that matters because it prevents wonder from becoming vague. It is easy to admire the universe in a general dreamy way and still keep it at a safe emotional distance. But the bent beam is not only a poetic curiosity in the heavens, it belongs to the same physical order that governs your world. The same laws that curve starlight also help determine whether your phone knows where you are. There is no sealed border between grand cosmic truth and practical earthly consequence. The world is one piece. Another lesson hidden here is about limits. Human beings often respond to mystery in two opposite and equally unhelpful ways. One is to pretend there is no mystery. The other is to inflate mystery until it becomes a kind of fog in which nothing can be known. This story avoids both. Light bending in gravity is initially mysterious, yes, but not unknowable. And even when we get to the stranger edges, what light experiences, black hole horizons, the special status of light-like paths, the mystery does not become a blank refusal. It becomes a boundary of language, a reminder that some questions need better phrasing. That is a healthier kind of mystery. It does not say stop thinking, it says think more carefully. That is worth remembering in a time when so many questions are pushed toward either overconfidence or fashionable confusion. The bent beam teaches a quieter discipline. Notice the puzzle, respect it. Do not force a quick answer just because your first intuition wants one. Let observation speak, let theory stretch. Be willing to trade a familiar picture for a better one. There are worse intellectual habits to learn before sleep, and then, perhaps, there is the most personal lesson of all. We measure our lives with time, movement, and perspective. We assume that the path between 2 points is simple if it looks simple. We assume that what appears straight probably is. We assume that the structure underlying everyday experience must be close to the one we imagine. Yet the universe keeps asking us to be gentler with our certainties. The beam that looked destined for a straight road turns out to have been following a curved one all along. It still arrived. It still made sense. But the deeper truth lay in the route, not the first appearance. There is something oddly encouraging in that. A thing can be bent without being broken. A path can curve without becoming meaningless. A journey can be shaped by forces you do not immediately see and still carry you where you need to go. That is not physics exactly, at least not in the narrow textbook sense, but it is a fair human echo of the scientific lesson. Reality is often more structured than it first appears, and understanding often comes from learning to see the hidden shape rather than insisting on the old straight line. Now, one must be careful not to become sentimental with a topic like this. Light does not care about our self-improvement. Galaxies are not arranging themselves to teach us resilience. A black hole is not a metaphor with an event horizon. The universe remains gloriously indifferent to our desire for tidy moral instruction. But indifference does not prevent insight. We are allowed to notice when a scientific truth also sharpens the way we think about certainty, perception, and the limits of simple stories. The bent beam is valuable because it is real. Any reflection it inspires must come second to that, and what a reality it is. A beam leaves a star. A massive body curves the space-time nearby. The path changes. The beam arrives from a direction different than flat intuition predicted. An eclipse reveals the shift. A theory survives. Galaxies become lenses. Dark matter maps itself through distortion. Black holes teach the ultimate severity of curved futures. All of that was hidden in the original little contradiction. Gravity should not bend light if light has no mass. Except that gravity was never merely what we thought. The contradiction was a doorway. Perhaps that is the quietest lesson of all. Some of the best scientific questions begin as complaints against the universe, and end as corrections to ourselves. We say this should not happen, and reality patiently replies that the should belong to our model, not to the world. The beam bends anyway. It is our job to learn why. So if you're lying there now, a little drowsier than when we began, with stars and lenses and black holes drifting gently about in your mind, you might let the question settle one last time in its final calmer form. Light has no mass in the ordinary sense. Gravity bends it anyway because gravity is not merely a pull on heavy things. It is the shape of space-time itself, and light follows that shape with perfect obedience. The beam is not breaking the rules. It is revealing them, and perhaps that is a lovely note on which to leave it tonight. The world is stranger than first appearances suggest, but not less orderly. The straight road was never quite as straight as we thought, and yet the journey still made sense. Somewhere above you, perhaps hidden by clouds, perhaps blazing clearly in the night, starlight is crossing curved paths at this very moment, arriving from deep time by routes shaped by gravity. Some of it has passed stars, some galaxies, some perhaps things darker and denser than anything the eye could ever name directly. And still it comes, quietly, lawfully, carrying the structure of the universe in the direction from which it arrives. So wherever you are listening from tonight, and whatever hour has found you there, I hope this strange little detour through bent light has given your thoughts something gentle to rest on. If it did, I would be very grateful if you liked the video, perhaps subscribed, and shared this calm corner of physics with someone else who might enjoy wandering their way towards sleep. And now, with the beam bent and the lesson tucked inside it, you may let the mind loosen its grip a little. The stars will go on sending their light, gravity will go on shaping the road, and for the moment at least there is nothing more you need to solve. Sleep well, wherever and whenever you are.